Hello there. It is good to have you with us again. Tonight, we are asking a question that has puzzled astronomers for decades. What happens when you travel so far from everything that even emptiness becomes the defining feature of space? We are venturing into the cosmic voids, regions so devoid of matter that a single hydrogen atom might drift for millions of years before encountering another. Our journey begins here, in the familiar glow of the Milky Way, where 400 billion stars crowd together in a disk 100,000 light-years across. From this dense stellar neighborhood, we will travel outward, past the local group of galaxies, through the great walls and filaments of the cosmic web, until we reach places where the distance between galaxies stretches to hundreds of millions of light-years. Places where the universe reveals its true structure, not as a uniform scattering of stars, but as a vast foam of matter surrounding enormous bubbles of almost nothing. Along the way, we will explore the physics that shaped these voids. We will learn why gravity, the same force that holds you gently to the Earth, has spent 14 billion years sculpting the universe into this intricate pattern of dense clusters and empty expanses. If these quiet explorations help you find rest at the end of a long day, please consider liking the video and subscribing to the channel. It helps others find their way here too. Now settle in. Let your breathing slow. The stars are waiting, and we have a very long way to travel together. The universe extends in every direction, and in every direction, it asks us to reconsider what we mean by distance. On Earth, distance is simple. A kilometer is a kilometer. Light crosses that space in approximately 3 microseconds, and the ground beneath remains still. But the cosmos operates under different rules, rules that bend intuition and stretch the meaning of far beyond recognition. Consider first the speed of light itself. At 299,792 kilometers per second, it represents the fastest possible transmission of information through space. Nothing with mass can reach this velocity. Nothing without mass can exceed it. This is not a technological limitation, but a fundamental property of space-time, woven into the equations that govern reality. When astronomers speak of a light year, they describe the distance light travels in 1 Earth year, roughly 9.46 trillion kilometers. This unit exists because human-scale measurements collapse into meaninglessness at cosmic proportions. The nearest star system to our Sun, Alpha Centauri, lies 4.37 light-years away. This means the light arriving at Earth tonight departed that triple star system in early 2021. We see Alpha Centauri not as it is, but as it was. This delay, this temporal displacement, compounds with distance until observation becomes archaeology. But here, a complication emerges. The universe is not static. It expands. In 1929, Edwin Hubble documented a peculiar relationship between distant galaxies and their light. The farther a galaxy lay from Earth, the more its light shifted toward the red end of the spectrum. This red shift indicated motion away from us, and the pattern held in every direction. Galaxies were not simply drifting apart like debris from an explosion. Space itself was stretching, carrying galaxies along like raisins in rising bread dough. The Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec, quantifies this expansion. A megaparsec equals 3.26 million light-years. So a galaxy 1 megaparsec away recedes from us at roughly 70 kilometers per second. A galaxy 2 megaparsecs distant recedes at 140 kilometers per second. The relationship scales linearly, and at sufficient distances, the implications become profound. At approximately 14.4 billion light-years, the recession velocity of space equals the speed of light. Beyond this threshold, space expands faster than light can traverse it. Photons emitted from objects past this boundary swim against a current too strong to overcome. They travel toward us at light speed, yet the space between us grows faster still. Like a swimmer in a river flowing backward faster than they can stroke forward, these photons make progress that is immediately erased. This boundary carries a name: the cosmic event horizon. Objects crossing beyond it become permanently unreachable. No signal we send will ever arrive. No light they emit will ever reach our instruments. They are not destroyed. They are not hidden behind matter. They simply exist in a region of space that expands away from us faster than causality permits contact. The observable universe, then, is not the whole universe. It is merely the sphere from which light has had time to reach us since the cosmos began. This sphere has a radius of approximately 46.5 billion light-years, a number that seems to contradict the universe's age of 13.8 billion years. The discrepancy resolves through expansion. Light that departed a distant galaxy 13 billion years ago traveled through space that continued stretching during the journey. The galaxy that emitted that light has since moved even farther away, carried by the expansion itself. When astronomers observe a galaxy at a redshift of z equals 10, they see light that left when the universe was approximately 480 million years old. That light has traveled for over 13 billion years. But the galaxy itself, if it still exists, now sits roughly 31 billion light-years from Earth. The light tells us where the galaxy was, not where it is. This distinction between look-back distance and co-moving distance matters deeply. Look-back distance measures the path the light traveled. Co-moving distance measures the current separation, accounting for all the expansion that occurred during transit. The two diverge dramatically at high redshifts. Temperature also plays a role in these calculations. The cosmic microwave background radiation, the oldest light detectable, began its journey when the universe cooled to approximately 3000 Kelvin, allowing atoms to form and photons to travel freely. That radiation has been stretched by expansion until its peak wavelength now corresponds to a temperature of just 2.725 Kelvin, mere degrees above absolute zero. The stretching of light is the stretching of space made visible, and so distance in cosmology becomes layered. There is the distance light has traveled, measured in years. There is the distance to where an object sits now, measured in light years but corrected for expansion. There is the distance beyond which objects can never be reached, defined by the rate of cosmic acceleration. Each measurement answers a different question, and each reveals a different truth about our isolation. The universe contains an estimated 2 trillion galaxies within the observable volume. Beyond the cosmic horizon, statistical models suggest far more, perhaps infinitely more, depending on the geometry of space itself. These galaxies exist. Their stars burn. Their planets orbit. But they lie beyond the edge of observation, separated from us not by walls or voids, but by the fundamental structure of expanding space-time. This is the nature of cosmic distance. It is not merely vast. It is active, growing, and in many cases, insurmountable. The light we collect tonight carries information from the past, and some of that past has already slipped beyond our future reach. The universe reveals itself in fragments, bounded by physics, and what lies beyond the boundary remains forever unknown. In December of 1995, astronomers made a decision that seemed, at first, counterintuitive. They pointed the Hubble Space Telescope at nothing. Not at a known galaxy, not at a nebula, not at any catalogued object of interest. They chose a patch of sky in the constellation Ursa Major, a region so empty that ground-based telescopes showed only darkness. The selected area measured roughly 5.3 square arc-minutes, equivalent to the apparent size of a tennis ball viewed from 100 meters away. To the casual observer, this fragment of sky contained nothing worth examining. The telescope held its gaze on this emptiness for 10 consecutive days, accumulating light in exposures that totaled approximately 150 hours. During this time, Hubble orbited Earth 342 times, and with each pass, its instruments gathered photons that had traveled billions of years to arrive at precisely that moment, at precisely that mirror. What emerged from this seemingly empty void changed our understanding of the universe. The resulting image, known as the Hubble Deep Field, revealed approximately 3,000 galaxies in a region of sky smaller than a grain of sand held at arm's length. These were not nearby objects. Many of these galaxies emitted their light when the universe was less than 1 billion years old, their photons traveling across 12 to 13 billion light-years of expanding space before striking Hubble's sensors. Each faint smudge in the image represented not a star, but an entire galaxy containing hundreds of billions of stars, each potentially hosting planetary systems, each burning through nuclear fusion cycles that would eventually scatter heavy elements into the cosmos. The physics of this observation reveals something profound about the nature of light collection. A photon is a discrete packet of electromagnetic energy, and it travels through vacuum at precisely 299,792.458 kilometers per second. This speed is constant, invariant, the same for every observer in every reference frame. When a photon leaves a distant galaxy, it carries information about that galaxy's state at the moment of emission. The photon does not age, it does not decay. It simply propagates through space-time until it encounters matter. But space-time itself is not static. During the billions of years these photons traveled toward Earth, the universe expanded. The wavelength of each photon stretched with the expanding fabric of space, a phenomenon called cosmological redshift. A photon emitted as ultraviolet light might arrive as visible light. A photon emitted as visible light might arrive as infrared. The degree of this stretching directly correlates with the distance traveled and the time elapsed, providing astronomers with a cosmic clock embedded in the light itself. The most distant galaxies in the Hubble Deep Field exhibit redshifts approaching Z equals 6, meaning their light has been stretched to 7 times its original wavelength. At this redshift, the look-back time exceeds 12.9 billion years. The The light captured by Hubble left these galaxies when the universe was approximately 900 million years old, less than 7% of its current age. These galaxies appear as they existed during the epoch of reionization, a period when the first generation of stars was flooding the cosmos with ultraviolet radiation, ionizing the neutral hydrogen that had filled intergalactic space since the cosmic dark ages. The galaxies themselves appear irregular, clumpy, smaller than modern spirals and ellipticals. This is not an artifact of distance or resolution. These are genuinely young systems, still assembling through mergers and accretion, their structures not yet settled into the elegant forms we observe in the local universe. Some appear blue, indicating active star formation, their light dominated by hot, massive stars burning through their hydrogen fuel at prodigious rates. Others appear red, their light shifted by expansion, their stellar populations already aging even in this early epoch. Consider the journey of a single photon from one of these distant galaxies. It begins in the outer atmosphere of a star, perhaps a blue supergiant with a surface temperature of 25,000 Kelvin, fusing hydrogen into helium at a rate that will exhaust its core within a few million years. The photon emerges with a wavelength of approximately 400 nanometers, placing it in the violet portion of the visible spectrum. It leaves the star's photosphere and enters the interstellar medium of its host galaxy, passing through clouds of gas and dust, occasionally scattering off electrons but mostly traveling unimpeded. The photon exits the galaxy and enters intergalactic space. Here, the density of matter drops to approximately 1 atom per cubic meter, a vacuum more perfect than anything achievable in terrestrial laboratories. The photon continues, its path straight, its speed constant, but the space through which it travels is expanding. With each passing billion years, the photon's wavelength increases, its energy decreases, its color shifts toward the red end of the spectrum. By the time this photon approaches the Milky Way, 12.9 billion years have passed. The universe has expanded by a factor of 7. The photon's wavelength has stretched from 400 nanometers to 2,800 nanometers, shifting from violet light to infrared radiation invisible to human eyes. The star that emitted this photon has long since exploded as a supernova, scattering iron and oxygen and carbon into the interstellar medium. The galaxy that hosted that star has merged with dozens of other galaxies, its identity subsumed into a larger structure. Nothing remains of the original source except this photon and its siblings, still propagating through the cosmos, carrying information about a moment that no longer exists anywhere in the universe. The photon enters the Milky Way's halo, passes through the sparse outer regions of our galaxy, and continues toward the inner disk. It approaches Earth's orbit, enters the planet's gravitational sphere of influence, and encounters the Hubble Space Telescope at an altitude of 547 kilometers above the surface. The photon strikes the telescope's 2.4-meter primary mirror, reflects to the secondary mirror, and is directed into one of the onboard instruments. There, it is absorbed by a charge-coupled device, liberating an electron that is counted, recorded, and stored as a single digit in a vast array of data. This single photon, one among trillions collected during the deep field observation, contributes to a pixel in the final image. That pixel, combined with millions of others, reveals the faint smudge of a galaxy that existed when the universe was young. The information encoded in that photon, the temperature of the star, the composition of its atmosphere, the motion of its host galaxy, becomes accessible to astronomers who will never see the original source, who study only the ancient light that survived the journey. The Hubble Deep Field demonstrated that the universe is not merely vast, but densely populated across its entire observable volume. Extrapolating from this single image, astronomers estimated that the observable universe contains approximately 200 billion galaxies, a number later revised upward to 2 trillion when deeper observations revealed fainter, smaller systems. Each of these galaxies represents a collection of matter that has been evolving for billions of years, forming stars, building heavy elements, assembling the raw materials from which planets and eventually life might emerge. Yet the deep field also revealed the limits of observation. The most distant galaxies in the image appear as mere specks, their light so faint and so red-shifted that detailed study becomes impossible. Beyond a certain distance, galaxies fade below the detection threshold, not because they cease to exist, but because their light has been stretched and diluted beyond recovery. The deep field peers deep into cosmic history, but it cannot see everything. The universe extends beyond the frame, beyond the sensitivity of any instrument, into regions where light has not yet had time to reach us, or where expansion has carried objects beyond our cosmic horizon. The observation required extraordinary precision. Hubble had to maintain its pointing accuracy to within 0.007 arc-seconds, roughly equivalent to holding a laser beam steady on a dime from 320 kilometers away. Any drift would smear the faint galaxies into undetectable blurs. The telescope's gyroscopes, reaction wheels, and fine guidance sensors worked in concert to achieve this stability, compensating for the gentle torques imparted by solar radiation pressure and the gravitational gradients of Earth's orbit. The data returned from this observation filled storage systems and occupied astronomers for years. Each galaxy in the image became a subject of study, its redshift measured, its morphology classified, its stellar population modeled. The deep field spawned follow-up observations, deeper exposures, wider surveys. It demonstrated that empty sky is never truly empty, that every direction we look contains galaxies beyond counting, each one a universe unto itself, each one separated from us by distances that light requires billions of years to cross. Among those billions of galaxies scattered across the Hubble Deep Field and its successors, one object emerged that pushed the boundaries of what astronomers believed possible. Its light had traveled so far, had been stretched so severely by the expansion of space itself, that when it finally arrived at our telescopes, it carried information from an era when the universe was barely recognizable. GNZ11 sits at a redshift of 11.09. That number, seemingly abstract, encodes an extraordinary physical reality. When light left this galaxy, the universe was approximately 400 million years old. The photons that eventually reached the Hubble Space Telescope, and later the James Webb Space Telescope, had been traveling for 13.4 billion years, crossing a cosmos that expanded beneath them the entire time. The galaxy itself, due to this expansion, now lies approximately 32 billion light-years away from Earth, a distance that exceeds the age of the universe multiplied by the speed of light, because space itself has been stretching during the journey. The physics of redshift explains how this works. Light travels as a wave, with peaks and troughs separated by a characteristic wavelength. When that light moves through expanding space, the fabric of space-time itself stretches, and the wavelength stretches with it. A photon that left GNZ11 with a wavelength in the ultraviolet range, around 121.6 nanometers corresponding to the Lyman alpha emission line of hydrogen, arrived at Earth with a wavelength of approximately 1,470 nanometers, deep in the infrared. The ratio of these wavelengths, -1, gives the redshift value. The original wavelength multiplied by 12.09 equals the observed wavelength, and so Z equals 11.09. This stretching is not a Doppler effect in the traditional sense. The galaxy is not moving through space at tremendous velocity like a car speeding away on a highway. Instead, the space between us and the galaxy has been expanding, carrying the galaxy with it, while simultaneously stretching the wavelength of any light crossing that space. The distinction matters because it means there is no limit to how fast the distance between us and GNZ11 can grow. The recession velocity, calculated from the Hubble constant of approximately 70 kilometers per second per megaparsec, suggests that GNZ11 is currently receding from us at roughly 2.3 times the speed of light. This does not violate relativity because nothing is moving through space faster than light. Space itself is expanding, and there is no speed limit on that expansion. The galaxy itself, as observed, appears remarkably compact. Its stellar mass has been estimated at approximately 1 billion solar masses, roughly 1% of the Milky Way's stellar content. Yet within that modest mass, star formation was occurring at a furious rate, producing new stars at approximately 24 solar masses per year. The Milky Way, by comparison, forms only 1 to 3 solar masses of new stars annually. This intense activity was typical of galaxies in the early universe, when dense clouds of primordial hydrogen and helium collapsed rapidly under gravity, igniting fusion in stars that burned hot and bright and brief. The spectrum of GNZ11 reveals the chemical fingerprints of this era. Hydrogen dominates, as expected, but the presence of heavier elements tells a story of stellar generations already completed. Carbon, nitrogen, and oxygen appear in the spectral lines, elements that can only be forged in the cores of massive stars and distributed through supernova explosions. For these elements to exist in GNZ11, stars must have already lived and died within the first few 100 million years of cosmic history. The most massive stars, those exceeding 8 solar masses, burn through their hydrogen fuel in mere millions of years, then explode, seeding the surrounding gas with the products of nucleosynthesis. GN-Z11 represents a snapshot of this process in action, a galaxy already enriched by the deaths of its first stellar generation. The temperature of the universe at the time light left GN-Z11 was approximately 30 Kelvin, nearly 10 times warmer than today's cosmic microwave background temperature of 2.7 Kelvin. This warmth came from the residual heat of the Big Bang, still dissipating as space expanded and cooled. The intergalactic medium was denser then, with hydrogen atoms more closely packed, and the process of reionization was underway. The first stars and galaxies were producing enough ultraviolet radiation to strip electrons from hydrogen atoms throughout the cosmos, transforming the universe from an opaque fog to the transparent void we observe today. GNZ11 likely contributed to this reionization. Its young, hot stars, many of them exceeding 50 solar masses, would have emitted copious ultraviolet photons capable of ionizing hydrogen at great distances. The galaxy sits in an era called the Epoch of Reionization, a transitional period lasting from roughly 150 million to 1 billion years after the Big Bang, during which the universe's hydrogen was gradually ionized by the accumulated radiation of the first luminous objects. Detecting GNZ11 required extraordinary sensitivity. The galaxy's apparent magnitude in the infrared is approximately 25.8, meaning it appears roughly 100 million times fainter than the faintest stars visible to the naked eye. The Hubble Space Telescope's Wide Field Camera 3, operating in the near-infrared, first identified the object as a candidate for extreme redshift. Subsequent spectroscopic observations confirmed the redshift value by identifying the characteristic break in the spectrum where hydrogen absorption cuts off light at wavelengths shorter than Lyman alpha. This Lyman break technique has become a standard tool for identifying distant galaxies, relying on the predictable behavior of hydrogen to create a spectral signature that shifts predictably with redshift. The light from GNZ11 carries information about conditions that no longer exist anywhere in the observable universe. The density of matter, the temperature of the cosmic background, the rate of star formation, the chemical composition of galaxies, all have changed dramatically in the 13.4 billion years since those photons began their journey. In a very real sense, GN-Z11, as we observe it, no longer exists. The galaxy has evolved, merged with neighbors, formed new generations of stars, possibly developed structures we would recognize as spiral arms or elliptical bulges. What we see is a fossil, a preserved image of youth, forever fixed at 400 million years after the beginning. And yet, even as GNZ11 held the record for the most distant spectroscopically confirmed galaxy, astronomers knew that the universe had more to reveal. The James Webb Space Telescope, launched in December 2021 and positioned at the second Lagrange point some 1.5 million kilometers from Earth, carried instruments specifically designed to push deeper into the infrared spectrum, to capture light that had been stretched beyond the reach of Hubble's detectors. Within its first years of operation, Webb would shatter the distance record repeatedly, each new discovery pushing closer to the theoretical limits of galaxy formation itself. The JADIS program, the JWST Advanced Deep Extragalactic Survey, represented one of the most ambitious observational campaigns ever undertaken. Astronomers dedicated over 800 hours of Webb's precious observation time to two small patches of sky, one in the constellation Fornax and one near the north ecliptic pole. The goal was straightforward in concept but staggering in ambition: to find the first galaxies, the objects that formed when the universe was still assembling itself from primordial hydrogen and helium, before heavy elements existed in any meaningful quantity, before the cosmic web had fully crystallized into the structure we observe today. In early 2024, the JD's team announced a discovery that redefined our understanding of early cosmic history. The object designated JD's GSZ 14-0 appeared as little more than a faint smudge in the infrared images, a collection of photons so sparse that each one represented a precious messenger from an almost inconceivably distant past. Spectroscopic analysis revealed a redshift of approximately 14.32, meaning the light had been stretched by a factor of more than 15 times its original wavelength. This single number carried profound implications. The photons reaching Webb's detectors had left their source roughly 290 million years after the Big Bang, when the universe was barely 2% of its current age. To grasp what this means requires understanding the timeline of cosmic evolution. The Big Bang occurred 13.8 billion years ago. For the first 380,000 years, the universe existed as a hot, opaque plasma, a fog of free electrons and protons too energetic to combine into neutral atoms. Light could not travel freely through this medium. Photons scattered constantly off the charged particles, creating a wall of opacity that no telescope can penetrate. Only when the universe cooled to approximately 3,000 Kelvin did electrons and protons finally combine to form neutral hydrogen, an event cosmologists call recombination. The universe became transparent, and the first light was released. Light we now detect as the cosmic microwave background radiation, stretched by expansion to microwave wavelengths, corresponding to a temperature of just 2.725 Kelvin. After recombination came the cosmic dark ages, a period lasting perhaps 100 to 200 million years, during which no stars existed. The universe contained only neutral hydrogen and helium gas, slowly cooling and gradually clumping under the influence of gravity. Dark matter, which outmasses ordinary matter by a factor of roughly 5 to 1, provided the gravitational scaffolding, creating wells of potential energy into which ordinary matter could fall. But the process was slow. Density fluctuations had to grow, gas had to cool, and the first stars had to somehow ignite in an environment utterly unlike anything that exists today. JADES-GS-Z14-0 represents light from just 290 million years into this 13.8 billion year history. The universe at that moment was roughly 50 times denser than it is today. The cosmic microwave background radiation, which now bathes all of space at 2.725 Kelvin, was then approximately 40 Kelvin, warm enough to affect the cooling of gas clouds. The first generation of stars, the so-called population 3 stars, had likely formed only tens of millions of years earlier. Massive objects, perhaps 100 to 1,000 times the mass of our Sun, burning through their hydrogen fuel in just a few million years before exploding as supernovae and seeding the universe with the first heavy elements. What makes JD's GSZ 14-0 remarkable is not merely its distance, but its unexpected brightness and size. At a redshift of 14.32, astronomers expected to find only the faintest, most primitive objects, perhaps individual star clusters or the very first proto-galaxies still in the process of assembly. Instead, they found a galaxy spanning approximately 1,600 light-years in diameter, already containing a substantial stellar population, already producing light at a rate that implies vigorous star formation. The object's intrinsic brightness, corrected for the enormous distance, suggests it was forming stars at a rate of several solar masses per year, comparable to modest star-forming galaxies in the much later universe. This presents a puzzle that astronomers are still working to resolve. Standard models of galaxy formation predicted a more gradual buildup of structure, a slow accumulation of mass over hundreds of millions of years. JDES GS-Z14-0 suggests that at least some regions of the early universe assembled galaxies with surprising speed, that the processes of gas cooling, collapse, and star formation operated more efficiently than theoretical models had anticipated. The discovery has prompted revisions to simulations of early cosmic structure, adjustments to the assumed efficiency of star formation in pristine gas, and renewed interest in the role of dark matter halos in accelerating gravitational collapse. The light from JD's GS-Z14-0 carries chemical signatures that speak to its primitive nature. Spectroscopic analysis reveals emission lines consistent with hydrogen and possibly oxygen, but the overall metallicity, the abundance of elements heavier than helium, appears to be extremely low. This is precisely what astronomers expect from galaxies forming in the early universe, before multiple generations of stars had lived and died, before supernovae had enriched the interstellar medium with carbon, nitrogen, oxygen, and the heavier elements that would eventually form planets and life. The stars in JD's GS-Z14-0 were burning fuel that was almost entirely hydrogen and helium, the raw materials left over from the Big Bang itself. The co-moving distance to JD's GS-Z14-0 exceeds 33 billion light-years. The galaxy, as it exists today, 13.5 billion years after the light we observe was emitted, has certainly evolved beyond recognition. It has merged with neighboring systems, formed countless new generations of stars, developed a chemical complexity that the young object we observe could not have possessed. The stellar population we see in Webb's images has long since died, their nuclear fires extinguished billions of years ago, their matter recycled into new stars, new planets, perhaps new forms of complexity we cannot imagine. And the recession velocity continues. At a redshift of 14.32, the galaxy was already receding from our location at many times the speed of light, carried away by the expansion of space itself. Today, that recession has only accelerated. The photons that left JD's GS-Z14-0 after the ones we are now detecting will never reach us. They are fighting against an expansion that grows faster with every passing moment, stretched ever further toward the red, their energy diminishing asymptotically toward zero. In the far future, even the memory of this galaxy will fade from our observable universe, its light red-shifted beyond detection, its existence erased from any possible record. This stretching of light, this gradual reddening of photons as they cross the cosmos, is not merely an observational curiosity. It is the universe revealing its own expansion, written in the wavelengths of every distant source we detect. To understand how galaxies like JD's GSZ 14-0 can appear so profoundly shifted from their original colors, we must examine the mechanism itself, the physics that transforms blue light into red, and eventually into wavelengths our eyes could never perceive. When a galaxy emits light, that light carries a specific wavelength determined by the physical processes within the source. Hydrogen atoms transitioning between energy states release photons at precise frequencies. The Lyman alpha emission line, produced when an electron falls from the second energy level to the first, emerges at a wavelength of 121.567 nanometers, deep in the ultraviolet. This is a fixed value, determined by the quantum mechanics of hydrogen, the same in a laboratory on Earth as in a galaxy 13 billion light-years away. The atom does not know where it is in the universe. It simply follows the rules of physics. But as that photon begins its journey across space, something happens. The fabric of space itself is not static. It expands. And as it expands, the photon traveling through it is stretched along with it. The wavelength grows longer. What began as ultraviolet light gradually shifts toward the visible spectrum, then into the red, then beyond into the infrared. The photon loses no energy to any external force. No collision occurs, no absorption and re-emission. The stretching is intrinsic to the geometry of the universe itself. This is cosmological redshift, and it differs fundamentally from the Doppler effect we experience with sound or with objects moving through space. When an ambulance passes on a highway, its siren sounds higher in pitch as it approaches and lower as it recedes. This is because the sound waves are compressed or stretched by the motion of the source through the medium of air. The ambulance is moving through space, and the observer is stationary within that same space. The Doppler effect describes relative motion within a fixed framework. Cosmological redshift operates differently. The distant galaxy is not moving through space away from us. Rather, the space between us and the galaxy is itself expanding. The galaxy may be nearly stationary relative to the local fabric of space-time, drifting only slightly due to gravitational interactions with its neighbors. But the cumulative expansion of all the space between us and that galaxy causes the light to stretch. It is as if the photon were traveling across a rubber sheet that someone is slowly pulling from both ends. The photon does not speed up or slow down relative to the sheet. It continues at the speed of light, 299,792 kilometers per second. But the sheet grows beneath it, and the wavelength of the photon grows with it. The mathematical relationship is elegant. The redshift value, denoted by the letter Z, describes how much the wavelength has stretched. A redshift of Z equals 1 means the wavelength has doubled. The universe was half its current size when that light was emitted. A redshift of Z equals 2 means the wavelength has tripled, and the universe was 1/3 its current size. For JD's GSZ 14-0, with a redshift of 14.32, the wavelength has stretched by a factor of 15.32. Light that began as ultraviolet at 121 nanometers now arrives at approximately 1,860 nanometers, deep in the infrared, invisible to human eyes but detectable by the instruments aboard the James Webb Space Telescope. This relationship also tells us about the scale factor of the universe at the time of emission. When that light left JADES-GS-Z14-0, the universe was only about 6.5% of its current size. Every distance we measure today was compressed by that same factor. The space between galaxies, the voids between clusters, the entire cosmic web, all were packed into a volume roughly 15 times smaller in each linear dimension. The density of matter was correspondingly higher, the temperature of the cosmic background radiation was hotter, and the conditions for star formation were profoundly different from what we observe in the nearby universe. The expansion of space is governed by the Hubble constant, a value that describes how quickly distant objects appear to recede from us. Current measurements place this constant at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.26 million light-years, the recession velocity increases by 70 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second. And at sufficient distances, this recession velocity exceeds the speed of light itself. This does not violate relativity. Nothing is moving through space faster than light. The galaxies are nearly stationary relative to their local space-time. But the space between us and those galaxies is accumulating new distance faster than light can cross it. The photons are still traveling at 299,792 kilometers per second relative to the space immediately around them. But the total amount of space they must cross is growing faster than they can traverse it. It is like walking forward on a treadmill that accelerates beneath your feet. You are still walking at the same pace, but the destination recedes faster than you can approach it. For objects at the most extreme red shifts, this creates a peculiar situation. The light we receive from JADES-GS-Z14-0 was emitted when the universe was much smaller, when the recession velocity at that distance was lower. The photons were able to make progress toward us because the expansion was slower in the past. But as they traveled, the universe continued to expand, and the space behind them grew faster than the space ahead. They were, in a sense, surfing on the edge of a wave, carried forward by the geometry of an expanding cosmos. Had they been emitted slightly later, from a galaxy slightly farther away, they might never have reached us at all. The energy of a photon is inversely proportional to its wavelength. As the wavelength stretches, the energy decreases. A photon that began with an energy of 10.2 electron volts, corresponding to the Lyman alpha transition, arrives after 13.4 billion years with an energy of only 0.67 electron volts, reduced by the same factor of 15.32. This energy has not been absorbed by anything. It has not been transferred to another particle. It has simply been diluted by the expansion of space, spread across a longer wavelength, a gentler oscillation of the electromagnetic field. This is why the most distant objects in the universe are invisible to optical telescopes. Their light has been stretched so far into the infrared that it passes through the visible spectrum entirely. The Hubble Space Telescope, with its optical and near-infrared instruments, could detect galaxies out to redshifts of approximately 11. Beyond that, the light shifted past its detection range. The James Webb Space Telescope, with its mid-infrared capabilities, can see further, detecting objects at redshifts of 14 and beyond. But even Webb has limits. At some point, the light stretches into wavelengths too long for any current instrument to detect, and the objects fade from our technological reach. And the stretching continues. Every photon currently traveling through intergalactic space is being stretched at this moment, its wavelength growing imperceptibly longer with each passing second. The light from distant galaxies that will arrive at Earth 1 billion years from now will be more red-shifted than the light arriving today. The universe is not slowing its expansion. It is accelerating, driven by the mysterious influence of dark energy, a component of the cosmos that constitutes approximately 68% of its total energy density. This acceleration means that the red-shifting will only intensify, that distant objects will fade more rapidly into the infrared, and that the observable universe will gradually empty of visible sources. This fading, this gradual disappearance of distant light into wavelengths beyond our instruments, points toward something more fundamental than mere technological limitation. It reveals the existence of a boundary in the cosmos, a threshold beyond which the universe becomes not merely difficult to observe, but physically impossible to reach. This boundary is the cosmic horizon, and it marks the edge of everything we can ever hope to see or touch, no matter how advanced our technology becomes or how long we wait. The cosmic horizon arises from a simple but profound conflict between two speeds: the speed of light and the speed at which space itself expands. Light travels at approximately 299,792 kilometers per second, a velocity that remains constant regardless of the motion of its source or observer. This speed limit, established by the structure of space-time itself, governs all electromagnetic radiation, all information transfer, all causal connection between events. Nothing carrying mass or information can exceed it. And yet, space itself is not bound by this restriction. The expansion of the universe is not movement through space, but the stretching of space itself, and this stretching can occur at any rate, including rates that exceed the speed of light. To understand this distinction, consider 2 points in the universe separated by a vast distance. The space between them is expanding, carrying them apart not because they are moving through a static background, but because the background itself is growing. The rate of this separation depends on the distance involved. The Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec, describes this relationship. For every megaparsec of distance, roughly 3.26 million light-years, the recession velocity increases by about 70 kilometers per second. At modest distances, this recession is negligible. A galaxy 10 megaparsecs away recedes at roughly 700 kilometers per second, a tiny fraction of light speed. But the relationship is linear, and the universe is vast. At a distance of approximately 4,200 megaparsecs, or about 13.7 billion light-years in terms of light travel time, the recession velocity reaches a critical threshold. Here, The expansion of space carries objects away from us at precisely the speed of light. This distance defines what cosmologists call the Hubble radius, or the Hubble sphere, a conceptual boundary surrounding every observer in the universe. Beyond this sphere, objects recede faster than light can travel toward us. They are not moving through space at superluminal velocities, which would violate relativity. Instead, the space between us and them is being created faster than light can cross it. The implications of this boundary are profound and counterintuitive. Light emitted by an object just beyond the Hubble radius, traveling toward us at its constant 299,792 kilometers per second, finds itself on a cosmic treadmill. It moves through local space at light speed, but the space it must cross is expanding faster than it can traverse. The photon makes progress in its immediate vicinity, but the total distance to its destination grows faster than it can close the gap. Such a photon, despite traveling at the maximum possible speed, will never reach us. It is running as fast as physics allows, yet falling behind. This creates a peculiar situation for objects near the Hubble radius. A galaxy at precisely this distance emits light that hangs in a kind of cosmic stasis, neither approaching nor receding, suspended in the expanding void. Galaxies slightly closer emit light that slowly gains ground, eventually reaching us after journeys of billions of years. Galaxies slightly farther emit light that falls inexorably behind, destined to wander the expanding universe forever without finding an observer. But the Hubble radius is not the true edge of the observable universe. The observable universe extends farther to what is called the particle horizon, currently located at a comoving distance of approximately 46.5 billion light-years. This larger boundary exists because the universe has a history, and that history includes periods when expansion was slower. Light emitted in the early universe, when the Hubble radius was smaller and expansion rates different, could cross into regions that would later be carried beyond the current Hubble sphere. Photons that began their journey billions of years ago, when the universe was denser and expansion slower, have been traveling toward us all this time, and some have succeeded in reaching us despite originating from regions now receding faster than light. The cosmic microwave background provides a vivid example. The photons of the CMB were released approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, allowing light to travel freely for the first time. At the moment of their release, these photons were much closer to our location in co-moving coordinates. The space between us and their point of origin has been expanding ever since, stretching to the current distance of about 45.5 billion light-years. The matter that emitted those photons is now receding from us at approximately 3 times the speed of light, carried by the expansion of space far beyond the Hubble radius. Yet the photons themselves, released when distances were smaller, have been traveling toward us all along, finally arriving after 13.8 billion years of cosmic wandering. This distinction between the Hubble radius and the particle horizon reveals something subtle about cosmic observation. We can see objects that are currently receding faster than light because we see them not as they are now, but as they were when their light began its journey. The light we receive from the most distant galaxies left its source when the universe was young, when those galaxies were much closer in commoving distance, when the Hubble radius encompassed them. We see their ancient past, frozen in photons that have been traveling ever since, while their present-day locations have long since crossed beyond any horizon we can reach. But there is another boundary, more absolute than the Hubble radius, more final than the particle horizon. This is the cosmic event horizon, and it represents the ultimate limit of future observation. The event horizon marks the distance beyond which light emitted today will never reach us, no matter how long we wait. Unlike the particle horizon, which describes what we can see from the past, the event horizon describes what we can ever hope to see from the future. And this horizon is shrinking. The accelerating expansion of the universe, driven by dark energy, ensures that the event horizon draws closer over cosmic time. Currently located at a commoving distance of approximately 16 billion light-years, this boundary represents the maximum distance from which a photon emitted at this moment could ever reach Earth. Light from galaxies beyond this distance, even light emitted right now, will never arrive. The expansion of space will carry it away faster than it can approach, condemning it to eternal wandering in an ever-expanding void. As the universe ages and expansion accelerates, this event horizon will contract. Galaxies that are currently within the event horizon will gradually cross beyond it, their future light lost to us forever. The observable universe will slowly empty, not because objects are being destroyed, but because they are being carried beyond the reach of any signal, any photon, any possible communication. The cosmos will grow lonelier with each passing eon, as more and more of its contents slip beyond the final horizon. This process of cosmic isolation has already begun. It is not a future event, not a theoretical possibility awaiting some distant epoch. Galaxies that were once visible from Earth, objects whose light once crossed the void to reach our corner of the cosmos, have already vanished beyond the observable boundary. They are lost to us now, their photons stretched into oblivion, their existence continuing in regions of space that will never again communicate with our own. To understand how this happens, consider a galaxy that emitted light toward Earth 10 billion years ago. At that moment, the universe was smaller, denser, and expanding at a different rate. The photon began its journey across a cosmos where distances were more modest, where the space between objects was compressed compared to today. But as that photon traveled, the universe expanded beneath it, stretching the fabric through which it moved. The galaxy that emitted the light was carried outward by this expansion, receding from Earth even as its photon approached. For billions of years, the photon made progress, crossing the growing void between its origin and its destination. But the expansion of space is not constant. It accelerates. Dark energy, that mysterious component comprising approximately 68% of the universe's total energy density, drives this acceleration. As the cosmos ages, the rate of expansion increases, and the recession velocity of distant objects grows faster. A galaxy that was receding at 50,000 kilometers per second 10 billion years ago may now be receding at 150,000 kilometers per second, carried outward by the accelerating expansion of the intervening space. For some galaxies, this acceleration has crossed a critical threshold. The light they emitted in the distant past managed to reach Earth, allowing astronomers to observe them, to measure their redshift, to catalogue their position in the cosmic web. But the light they are emitting now, the photons leaving their stars at this very moment, will never arrive. The expansion of space between that galaxy and Earth has accelerated to the point where new photons cannot make progress. They are emitted. They travel at 300,000 kilometers per second through local space. But the space itself is stretching faster than they can cross it. These photons will wander forever, red-shifting into longer and longer wavelengths, their energy draining away into the expanding void, never to reach any observer in our region of the cosmos. The galaxies themselves continue to exist. Their stars burn through their nuclear fuel, their planets orbit, their black holes consume matter and radiate energy. Nothing about their internal physics has changed. They have not been destroyed, have not faded from existence, have not undergone any catastrophic transformation. They have simply been carried beyond the reach of light itself, isolated by the geometry of an expanding universe. From their perspective, if any observers exist within them, our own Milky Way has similarly vanished, its light stretched beyond detection, its existence continuing in a region of space that has become forever inaccessible. Astronomers estimate that the observable universe currently contains approximately 2 trillion galaxies. But this number represents only those objects whose ancient light has managed to reach Earth, photons emitted when the universe was young enough and small enough for the journey to succeed. The actual universe, the totality of space and matter that exists beyond our observational horizon, may contain vastly more. Some cosmological models suggest that the full universe could be 250 times larger than the observable portion, containing perhaps 500 trillion galaxies or more. Others propose that the universe may be infinite in extent, containing an infinite number of galaxies stretching in every direction, the overwhelming majority forever hidden from our view. Among the galaxies we can currently observe, many have already crossed the event horizon. Their ancient light continues to arrive. Photons emitted billions of years ago, still completing their journey to Earth. But their present-day emissions are lost. The galaxy we see in a deep field image, its light having traveled 12 billion years to reach our telescopes, no longer occupies the position where we observe it. It has been carried outward by cosmic expansion, its current location perhaps 46 billion light-years from Earth, well beyond the event horizon of approximately 16 billion light-years. The image we capture is a ghost, a record of a past state, while the galaxy's present reality unfolds in a region of space that has become causally disconnected from our own. This disconnection is absolute. No signal traveling at or below the speed of light can cross the event horizon. No radio transmission, no laser pulse, no gravitational wave can bridge the gap. Even if an advanced civilization in one of these lost galaxies were to aim a beacon directly at Earth, pouring the energy of 1 trillion suns into a focused signal, that signal would never arrive. The expansion of space would stretch it, weaken it, redshift it into wavelengths beyond any possible detection, and ultimately carry it backward faster than it could advance. The laws of physics themselves enforce this isolation, not through any barrier or wall, but through the fundamental geometry of space-time in an accelerating universe. The rate at which galaxies cross beyond the event horizon will increase as cosmic acceleration continues. Currently, objects at the boundary are receding at approximately the speed of light, their photons hovering at the edge of progress. But as dark energy drives faster expansion, this boundary will contract, drawing closer to Earth. Galaxies that are currently well within the observable universe will gradually approach the horizon, their light growing fainter, their redshift increasing, until they too slip beyond the boundary and join the ranks of the lost. In approximately 100 billion years, if current models of cosmic acceleration hold, the only galaxies remaining within the observable universe will be those bound to our own local group by gravity. The Andromeda Galaxy, the Triangulum Galaxy, the various dwarf satellites orbiting the Milky Way. These objects, held together by their mutual gravitational attraction, will merge into a single, massive, elliptical galaxy. Everything else, every other galaxy in the current observable universe, will have crossed beyond the horizon, their light fading into the infinite redshift of an empty sky. But between those distant galaxies, between the superclusters and filaments that trace the large-scale structure of the cosmos, there exist regions of almost incomprehensible emptiness. These are the great voids, vast bubbles of near-nothingness that occupy the majority of the universe's volume, spaces so devoid of matter that a single atom might drift for millions of years without encountering another. The universe, when mapped at the largest scales, does not distribute its matter evenly. Galaxies cluster together, drawn by gravity into groups and clusters, which themselves aggregate into superclusters connected by filaments of dark matter and gas. This cosmic web, as astronomers call it, resembles soap foam in its structure. Thin walls and threads of matter surrounding enormous, empty bubbles. And it is within these bubbles that the great voids reside, regions where the density of matter falls to perhaps 1/10 the cosmic average, where galaxies are so scarce that one might travel hundreds of millions of light years without passing a single star. The Botas void, discovered in 1981 by Robert Kirshner and his colleagues, stretches approximately 330 million light-years across, making it one of the largest known structures in the observable universe. To comprehend this scale, consider that the Milky Way galaxy spans roughly 100,000 light-years. The Botas void could contain over 3,000 Milky Way diameters laid end to end. If our galaxy were reduced to the size of a small coin, the Botas void would stretch across a football field. Within this enormous volume, astronomers have detected only approximately 60 galaxies. In a region that should contain thousands based on the average cosmic density, only 60 isolated systems drift through the darkness. The average separation between these galaxies exceeds 10 million light-years, meaning that light from one galaxy would take 10 million years to reach its nearest neighbor. An observer on a planet within the Botas void would look up at a night sky almost entirely devoid of external galaxies, seeing only the stars of their own isolated system against an otherwise empty blackness. The physics that created these voids began in the earliest moments of the universe. Quantum fluctuations during the inflationary epoch, that brief period of exponential expansion in the first fraction of a second after the Big Bang, produced tiny variations in the density of matter. These variations, initially differing by only 1 part in 100,000, served as seeds for all future structure. Regions of slightly higher density attracted more matter through gravity, growing denser over time. Regions of slightly lower density lost matter to their denser neighbors, becoming progressively emptier. Over 13.8 billion years, this process amplified those initial quantum whispers into the cosmic web we observe today. Matter flowed along gravitational gradients, streaming from underdense regions toward overdense ones, like water draining from a landscape into rivers and lakes. The voids grew larger and emptier as their matter evacuated, while the filaments and clusters grew denser and more massive. The temperature within these voids differs measurably from denser regions. While galaxy clusters contain hot gas, heated to tens of millions of Kelvin by gravitational compression and shock waves, void interiors remain cooler, their sparse gas settling to temperatures of perhaps 1 million Kelvin or less. The cosmic microwave background radiation, that remnant glow from 380,000 years after the Big Bang, appears slightly colder when observed through voids due to the integrated Sachs-Wolf effect. Photons lose energy as they climb out of the gravitational potential wells created by the surrounding denser structures. The KBC void, named after Keenan, Barger, and Cowie, who characterized it in 2013, may be even more remarkable than Boötes. This structure, centered roughly on our own position in the universe, extends approximately 2 billion light-years in diameter, making it potentially the largest void ever identified. We appear to reside within an underdense bubble, a region where the galaxy density falls perhaps 20 to 40% below the cosmic average. This local underdensity may explain certain anomalies in measurements of the Hubble constant, the rate at which the universe expands as light traveling through less dense regions experiences different gravitational effects than light passing through average density space. The giant void, located in the direction of the constellation Canes Venatici, spans approximately 1.3 billion light-years and contains so few galaxies that its discovery in 1988 challenged existing models of structure formation. How could such enormous empty regions exist if matter were distributed according to standard cosmological assumptions? The answer lies in the statistical nature of quantum fluctuations and the amplifying power of gravity over cosmic time. Within these voids, the few galaxies that do exist tend to be smaller, bluer, and more actively forming stars than their counterparts in denser environments. Isolated from the gravitational harassment and gas stripping that occurs in clusters, void galaxies evolve more slowly, retaining their gas reservoirs and continuing to form new stars at modest rates. They represent a kind of cosmic time capsule, galaxies that have experienced less environmental processing than their clustered cousins. The darkness within these voids is not absolute. Intergalactic space, even in the emptiest regions, contains a thin fog of hydrogen and helium atoms, perhaps 1 atom per cubic meter on average. Cosmic rays, high-energy particles accelerated by distant supernova, and active galactic nuclei traverse these spaces at nearly the speed of light. The cosmic microwave background permeates every cubic centimeter, providing a faint bath of photons at a temperature of 2.725 Kelvin. And dark matter, that invisible substance comprising roughly 27% of the universe's energy density, fills the voids as well, though at lower concentrations than in the surrounding filaments. Yet for any hypothetical observer within a void, the isolation would be profound. The nearest major galaxy might lie 50 million light-years distant, its light requiring 50 million years to make the journey. Radio signals traveling at light speed would take equally long to cross the gulf. Any civilization arising within a void galaxy would face a universe that appears almost entirely empty, a cosmos where the great structures and teeming clusters exist only as faint smudges requiring the most powerful telescopes to detect. These voids continue to grow. As the universe expands and dark energy accelerates that expansion, matter continues to drain from underdense regions into overdense ones. The voids stretch larger, their boundaries pushing outward, their interiors growing emptier. In the far future, the great voids will merge and expand until they dominate the cosmic landscape entirely, leaving only isolated clusters of gravitationally bound galaxies separated by gulfs of nothingness that no signal could ever cross. Yet even within this cosmic architecture of filaments and voids, of galaxies bound to clusters and clusters bound to superclusters, individual stars sometimes break free entirely. They drift through the spaces between galaxies, unmoored from any gravitational home, traveling alone through regions where the nearest star might lie millions of light-years distant. These are the rogue stars, objects ejected from their birth galaxies through gravitational encounters so violent that they achieved escape velocity not merely from a solar system, but from an entire galaxy. The process begins, most commonly, in the dense stellar nurseries near galactic cores. In the central regions of a typical spiral galaxy like the Milky Way, stars crowd together at densities thousands of times greater than in the galactic suburbs where our own sun resides. Within the inner few parsecs of the galactic center, millions of stars orbit the supermassive black hole, their paths weaving through a gravitational environment of extraordinary complexity. Here, close encounters between stars occur frequently on astronomical timescales, and the presence of a 4 million solar mass black hole creates conditions for dramatic gravitational interactions. When a binary star system, two stars orbiting each other, passes too close to a supermassive black hole, the tidal forces can tear the pair apart. One star may be captured into a tight orbit around the black hole, or even consumed entirely. The other star, through the conservation of momentum and energy, receives a tremendous gravitational kick. This mechanism, first described theoretically by astronomer Jack Hills in 1988, can accelerate a star to velocities exceeding 1,000 kilometers per second, fast enough to escape not only the galactic core but the entire galaxy itself. The Milky Way's central black hole, Sagittarius, a star, has been ejecting stars through this process for billions of years. Observations have confirmed dozens of hypervelocity stars racing outward through the galactic halo, their trajectories traced backward to origins near the galactic center. The fastest confirmed example, designated S5HVS1, travels at approximately 1,755 kilometers per second relative to the galaxy. At this velocity, the star covers roughly 150 million kilometers every day, a distance greater than the Earth-Sun separation. Yet even at such speeds, the star requires millions of years to traverse the galaxy and enter intergalactic space. The physics of these ejections follows directly from orbital mechanics and energy conservation. In a three-body interaction involving two stars and a massive black hole, energy transfers between the participants. The black hole, with its enormous mass, acts as a gravitational slingshot. When the geometry aligns correctly, one star loses orbital energy and falls inward, while the other gains energy and is flung outward. The velocity imparted depends on how closely the binary approached the black hole and the masses involved. For the most extreme ejections, the departing star carries enough kinetic energy to overcome the gravitational binding energy of the entire galaxy. But supermassive black holes are not the only ejection mechanism. Dense stellar clusters, even those far from galactic centers, can produce runaways through purely stellar interactions. When three or more stars interact gravitationally in a close encounter, the mathematics of the three-body problem allows for chaotic energy exchange. One star may be ejected at high velocity, while the others form a tighter binary or fall into new orbits. Globular clusters, those ancient spherical collections of hundreds of thousands of stars orbiting in galactic halos, have been shedding members through such interactions for billions of years. The velocities achieved through cluster ejections typically range from tens to hundreds of kilometers per second, generally insufficient to escape the galaxy entirely, but enough to send stars on highly elliptical orbits through the galactic halo. Some fraction of these stars, particularly those ejected from clusters already in the outer halo, do achieve escape velocity. They drift outward, their velocities gradually decreasing as they climb out of the galactic gravitational well until they cross into true intergalactic space. Supernova explosions in binary systems provide another ejection pathway. When one star in a closed binary undergoes core collapse and explodes as a supernova, the explosion may be asymmetric, imparting a kick to the newly formed neutron star or black hole. But the companion star also receives a dramatic change in circumstances. The mass loss from the exploding star suddenly reduces the gravitational binding of the system. If the binary was tight enough and the mass loss sufficient, the companion star finds itself unbound, flying off at whatever orbital velocity it possessed at the moment of explosion. These runaway stars, identifiable by their high velocities and often by the bow shocks they create as they plow through interstellar gas, populate the galactic disk and halo. Once a star escapes its home galaxy, its fate becomes one of extraordinary isolation. Intergalactic space contains roughly 1 atom per cubic meter, a vacuum more perfect than anything achievable in terrestrial laboratories. The escaped star carries with it whatever planetary system it possessed. Any debris disk, any companions too small to detect. It drifts through this emptiness, its nuclear fires continuing to burn, its light radiating outward into a void where no other star exists within millions of light years. The journey of a rogue star through intergalactic space unfolds over timescales that dwarf human comprehension. A star ejected from the Milky Way at 1,000 kilometers per second would require approximately 3 million years to reach the Andromeda Galaxy, assuming it traveled directly toward our nearest large neighbor. Most ejected stars do not travel toward other galaxies. They move outward into the voids, into the spaces between galactic filaments, into regions where they may drift for billions of years without encountering any significant gravitational influence. During this drift, the star continues its normal stellar evolution. A sun-like rogue star would spend 10 billion years fusing hydrogen in its core, then expand into a red giant, shed its outer layers as a planetary nebula, and collapse into a white dwarf, all while traveling through intergalactic emptiness. The planetary nebula would expand and dissipate into the void, its atoms spreading through space that contains almost nothing else. The white dwarf would continue its journey, slowly cooling over trillions of years, its surface temperature dropping from tens of thousands of Kelvin toward the background temperature of the universe itself. Estimates suggest that intergalactic space contains a substantial population of these stellar wanderers. Simulations of galaxy formation and evolution indicate that gravitational interactions have ejected roughly 1 trillion stars into the voids between galaxies within the observable universe. This number, while enormous in absolute terms, represents only a tiny fraction of all stars. Spread across the vast intergalactic volumes, these rogue stars maintain average separations of millions of light-years from one another. Each drifts in isolation so complete that the light from the nearest neighboring rogue would take millions of years to arrive. Among these stellar wanderers drifting through intergalactic darkness, a particular class of rogue stars stands apart. These are the hypervelocity stars, objects moving so fast that they have escaped not merely their birth clusters or local stellar neighborhoods, but their entire home galaxies. Their velocities are extraordinary, reaching speeds of 500 to 1,000 kilometers per second, and in extreme cases exceeding 1,700 kilometers per second. At such speeds, a star could cross the distance from Earth to the Moon in roughly 4 minutes. These objects are not simply drifting through space. They are fleeing it, propelled by some of the most violent gravitational encounters in the universe. The mechanism that creates hypervelocity stars involves the supermassive black holes that lurk at the centers of galaxies. Sagittarius A star, the 4 million solar mass black hole at the heart of the Milky Way, serves as the primary engine for producing these cosmic projectiles. The process begins when a binary star system, 2 stars gravitationally bound to each other, wanders too close to the galactic center. Binary stars are common throughout galaxies, comprising roughly half of all stellar systems. As such a pair approaches the supermassive black hole, the gravitational field becomes increasingly extreme. At distances of a few hundred astronomical units from Sagittarius A star, the tidal forces become strong enough to tear the binary apart. This disruption follows precise gravitational physics. The black hole's gravity pulls more strongly on the nearer star than on the farther one, creating a differential force that exceeds the gravitational binding energy holding the pair together. In the moment of separation, one star typically falls inward, spiraling toward the black hole's event horizon. The other star, through the conservation of momentum and energy, receives a tremendous gravitational kick. It is flung outward at velocities that can exceed the escape velocity of the entire galaxy. The Milky Way's escape velocity at the solar radius is approximately 550 kilometers per second. Hypervelocity stars routinely exceed this threshold by factors of 2 or 3. The first hypervelocity star was discovered in 2005, designated SDSSJ09074 plus 024507. This object, located roughly 180,000 light-years from the galactic center, was found to be moving at approximately 850 kilometers per second relative to the Milky Way's rest frame. Tracing its trajectory backward through time revealed an origin consistent with the galactic center, with an ejection occurring roughly 80 million years ago. Since that initial discovery, astronomers have identified dozens of confirmed hypervelocity stars and hundreds of candidates. The Gaia Space Telescope, with its precise measurements of stellar positions and motions, has dramatically expanded this catalogue, revealing the full three-dimensional velocities of millions of stars and identifying those with trajectories pointing away from the galactic core. The physics of the ejection process, known as the Hills mechanism after astronomer Jack Hills, who predicted it in 1988, depends critically on the mass ratio between the black hole and the binary system, the orbital parameters of the binary, and the closest approach distance to the black hole. Simulations showed that the ejected star typically receives a velocity boost roughly equal to the orbital velocity of the original binary system, which can be several hundred kilometers per second for tight binaries. This boost adds to the velocity the binary already possessed from falling toward the black hole, resulting in the extreme speeds observed. Not all hypervelocity stars originate from supermassive black hole encounters. Some are produced by supernova explosions in binary systems, where the sudden mass loss and asymmetric explosion can impart significant kicks to surviving companion stars. Others result from gravitational interactions in dense stellar environments like globular clusters, where close encounters between multiple stars can occasionally eject one member at high velocity. However, the fastest hypervelocity stars, those exceeding 1,000 kilometers per second, almost certainly require the gravitational influence of a supermassive black hole. The star S5 HVS1, discovered in 2019, holds the current record for the fastest known hypervelocity star in the Milky Way. This object, an A-type main sequence star with a mass roughly 2.3 times that of the Sun, is traveling at approximately 1,755 kilometers per second. At this velocity, it will escape the Milky Way entirely and continue into intergalactic space, never to return. Tracing its trajectory backward indicates an ejection from the galactic center roughly 4.8 million years ago. The star is currently located about 29,000 light-years from the Sun, still within the Milky Way's halo, but moving outward at a rate that will carry it beyond the galaxy's gravitational influence within a few hundred million years. The journey of a hypervelocity star from galactic core to intergalactic void spans millions of years and hundreds of thousands of light-years. During this transit, the star continues its normal stellar evolution, fusing hydrogen in its core, maintaining its luminosity, aging according to its mass. A hypervelocity star ejected as a young, massive blue star might exhaust its fuel and explode as a supernova while still within the galactic halo, leaving behind a neutron star or black hole that continues the outward journey as a dark remnant. Lower mass hypervelocity stars, those similar to the Sun or smaller, will survive long enough to escape entirely, carrying their steady fusion fires into the intergalactic darkness. These stars serve as tracers of galactic dynamics, their trajectories encoding information about the mass distribution of the galaxy and the properties of the central black hole. By measuring the velocities and positions of hypervelocity stars, astronomers can constrain the total mass of the Milky Way, including its dark matter halo. The escape velocity at any given radius depends on all the mass interior to that point, so stars that have clearly escaped provide lower limits on the galaxy's total gravitational binding energy. The rate of hypervelocity star production in the Milky Way is estimated at roughly 1 ejection every 10,000 to 100,000 years. Over the galaxy's 13 billion-year history, this suggests that millions of stars have been flung into intergalactic space by encounters with Sagittarius A star. Most of these ancient ejections have long since traveled beyond any hope of detection, their light too faint, their distances too great. They drift now through the voids between galaxies, each carrying the chemical signature of its birth environment, each a messenger from a galactic core it will never see again. But stars are not the only objects cast adrift in the darkness between galaxies. Planets, too, wander through intergalactic space, worlds that have never known the warmth of a parent star or that were torn from their original orbits by gravitational encounters. These orphan planets, sometimes called rogue planets or free-floating planetary mass objects, represent one of the most thermodynamically extreme environments in the universe. They are worlds where the only significant energy input comes from within, where surface temperatures plunge toward the cosmic background, and where any atmosphere must eventually freeze and fall as snow onto landscapes of permanent night. The formation mechanisms for orphan planets are varied and well understood. Some form in the same manner as stars, through the gravitational collapse of molecular cloud fragments, but with masses too low to ignite hydrogen fusion. These are essentially failed stars, objects that condensed from interstellar gas but never achieved the 13 Jupiter masses necessary to sustain even deuterium burning. They cool gradually over billions of years, radiating away their formation heat into space, their surfaces dropping from thousands of Kelvin to mere tens of Kelvin over cosmological timescales. Other orphan planets began their existence in ordinary planetary systems, orbiting stars in configurations that proved gravitationally unstable. Multi-planet systems are inherently chaotic over long timescales. Gravitational perturbations accumulate, orbital resonances shift, and eventually one or more planets may be ejected entirely. Computer simulations of planetary system evolution suggest that ejection events are common, perhaps even typical. The average planetary system may expel one or more planets during its first few 100 million years, as the configuration settles into a stable arrangement. The numbers involved are staggering. Microlensing surveys, which detect planets by the brief brightening they cause when passing in front of background stars, suggest that orphan planets may outnumber stars in the Milky Way by a factor of 2 or more. This implies roughly 400 billion free-floating planetary mass objects in our galaxy alone, drifting through interstellar space without any stellar companion. Most of these objects are likely to have masses comparable to Jupiter or smaller, though some may approach the deuterium-burning threshold of 13 Jupiter masses. The thermodynamic situation of an orphan planet is fundamentally different from that of a planet orbiting a star. A world like Earth receives approximately 1,361 watts per square meter of solar radiation at its orbital distance. This energy input drives atmospheric circulation, maintains liquid water, and sustains the temperature differential between equator and poles that creates weather. Remove this external energy source, and the planet must rely entirely on internal heat to maintain any temperature above the cosmic background. For a rocky planet like Earth, internal heat comes primarily from 2 sources: the residual heat of formation, stored in the mantle and core, and the decay of radioactive isotopes such as uranium-238, thorium-232, and potassium-40. Earth's internal heat flow is approximately 0.087 watts per square meter, roughly 15,000 times less than the solar input. If Earth were suddenly ejected from the solar system, its surface temperature would plunge rapidly. Within weeks, the oceans would freeze. Within years, the atmosphere itself would begin to condense, with nitrogen and oxygen falling as snow onto a surface approaching 40 Kelvin. Yet internal heat could maintain liquid water beneath the surface for billions of years. Earth's geothermal gradient increases temperature by roughly 25 to 30 Kelvin per kilometer of depth. At sufficient depth, temperatures remain high enough for liquid water regardless of surface conditions. An orphan Earth might maintain a subsurface ocean beneath tens of kilometers of ice, heated from below by radioactive decay, potentially habitable for simple life forms that require no sunlight. Gas giant orphan planets face different thermodynamic constraints. Jupiter radiates approximately 1.67 times more energy than it receives from the Sun, powered by the slow gravitational contraction of its interior and the differentiation of helium sinking through metallic hydrogen. This internal heat source would persist regardless of stellar proximity. An orphan Jupiter would cool more rapidly without solar input, but its massive atmosphere would retain heat effectively. Surface temperatures in the upper cloud layers might drop from the current 165 Kelvin to perhaps 50 or 60 Kelvin over billions of years. But the deep atmosphere would remain warm, with temperatures exceeding 300 Kelvin at pressures of several bars. The detection of orphan planets presents significant observational challenges. Without a parent star to illuminate them or cause detectable wobbles, these objects reveal themselves only through their own faint thermal emission or through gravitational effects. Young orphan planets, still warm from formation, emit infrared radiation detectable by sensitive telescopes. The WISE infrared survey and subsequent missions have identified numerous candidate objects, including several within 30 light-years of the Sun. One particularly well-studied example is WISE 0855-0714, a brown dwarf or massive orphan planet located approximately 7.2 light-years from Earth. With an estimated mass of 3 to 10 Jupiter masses and a surface temperature of roughly 250 Kelvin, this object represents the coldest known free-floating body outside our solar system. Its atmosphere shows evidence of water ice clouds, the first such detection on an object outside the solar system. At 250 Kelvin, or roughly -23 degrees Celsius, this world is cold by terrestrial standards, but warm compared to the cosmic background temperature of 2.7 Kelvin. The ultimate fate of orphan planets is determined by thermodynamics. Without any external energy input, these worlds must eventually cool toward equilibrium with the cosmic microwave background. The timescale for this cooling depends on mass and composition. A Jupiter mass gas giant might require tens of billions of years to cool below 10 Kelvin, its massive atmosphere acting as an effective insulator. A rocky Earth mass planet would cool more rapidly, reaching equilibrium with the cosmic background within a few billion years once radioactive heating diminishes. At temperatures approaching 2.7 Kelvin, even hydrogen becomes a solid. An orphan planet that has cooled to cosmic background temperature would be a world of frozen gases, its atmosphere long since condensed onto the surface, its internal heat exhausted, its only remaining energy the faint trickle of cosmic ray interactions, and the even fainter heating from the cosmic microwave background itself. Such objects would be essentially undetectable, dark and cold, drifting through intergalactic space for timescales that dwarf the current age of the universe. Yet isolation in the cosmos operates at scales far larger than individual planets or wandering stars. Entire galaxies can find themselves alone, separated from their nearest neighbors by distances so vast that the universe itself appears empty from their vantage point. These are the loneliest galaxies, systems that formed or drifted into the great cosmic voids, and now exist in regions where the average density of matter falls to less than 1/10 the cosmic mean. The galaxy MCG plus 01-02-015, located approximately 300 million light-years from Earth in the direction of the constellation Pisces, exemplifies this profound isolation. It sits near the center of a void so empty that astronomers have measured no other galaxy of comparable size within 100 million light-years of its position. To comprehend this remoteness, consider that our own Milky Way has the Andromeda Galaxy as a neighbor at merely 2.5 million light-years, with dozens of smaller satellite galaxies scattered within a few 100,000 light-years. MCG plus 01-02-015 possesses no such companions. Its nearest substantial neighbor lies 40 times farther away than Andromeda lies from us. From a hypothetical planet within MCG plus 01-02-015, the night sky would present a fundamentally different character than the sky visible from Earth. The Milky Way's night sky contains approximately 6,000 stars visible to the naked eye, plus the luminous band of our galaxy's disk stretching across the heavens, plus the faint smudges of Andromeda and the Magellanic Clouds representing other galaxies. From the lonely galaxy in the void, observers would see their own stars, their own galactic disk if the galaxy possessed one. But beyond that boundary, the sky would be essentially black, No neighboring galaxies would be visible without powerful telescopes. The universe beyond their home galaxy would appear as a vast, uniform darkness. This isolation has measurable physical consequences. Galaxies in dense environments like the Virgo cluster, located 54 million light-years from Earth and containing over 1,300 member galaxies, experience frequent gravitational interactions. These encounters strip gas from galaxies, trigger bursts of star formation, distort galactic shapes through tidal forces, and occasionally result in full mergers. The Milky Way itself shows evidence of past interactions, including streams of stars pulled from absorbed dwarf galaxies and a future collision with Andromeda predicted to occur in approximately 4.5 billion years. Void galaxies experience none of this. They evolve in near-perfect isolation, their development governed almost entirely by internal processes rather than external influences. Studies of void galaxies revealed that they tend to be bluer in color than their counterparts in denser regions, indicating ongoing star formation. This occurs because their gas reservoirs remain intact, never stripped away by interactions with neighbors or the hot intergalactic medium that pervades galaxy clusters. A void galaxy retains its primordial hydrogen, converting it slowly into stars over billions of years, rather than losing it to environmental processes. The void galaxy KK246, also known as ESO 461-036, provides another example of extreme isolation. Located approximately 25 million light-years away, it sits within the local void, a region of significantly reduced galaxy density that borders our own local group. The local void spans roughly 150 million light-years and contains far fewer galaxies than would be expected for a region of that volume. KK246 drifts through this emptiness, a dwarf irregular galaxy with a mass perhaps 1,000th that of the Milky Way, forming stars at a leisurely pace from gas that has remained undisturbed for billions of years. The physics of void formation explains why these regions exist and why some galaxies find themselves trapped within them. In the early universe, quantum fluctuations during inflation created slight variations in matter density. Regions with marginally higher density attracted more matter through gravity, becoming denser still, while regions with marginally lower density lost matter to their denser neighbors. Over 13.8 billion years, this process amplified initial variations of perhaps 1 part in 100,000 into the cosmic web visible today, where density contrasts between filaments and voids can exceed factors of 100. Galaxies that formed in the underdense regions, or that were gravitationally nudged into expanding voids, found themselves increasingly isolated as cosmic expansion carried the surrounding structure away. The expansion of space itself contributes to void growth. A void 100 million light-years across expands at approximately 2,200 kilometers per second across its diameter, assuming a Hubble constant of 70 kilometers per second per megaparsec. Galaxies at the edges of voids feel a slight gravitational pull toward the denser walls and filaments, causing them to drift outward from the void center, leaving central regions even emptier. The Boötes void, one of the largest known voids in the observable universe, demonstrates the extremity of cosmic emptiness. Discovered in 1981, It spans approximately 330 million light-years and contains only about 60 known galaxies, whereas a region of average density that size would contain roughly 2,000 galaxies. The galaxies within the Botas void cluster along a thin filament that threads through the emptiness, leaving most of the void's volume essentially devoid of luminous matter. For a galaxy at the center of the Botas void, the nearest large galaxy cluster would lie over 150 million light-years away. Light from that cluster would take 150 million years to arrive, meaning observers in the void galaxy would see their distant neighbors not as they are, but as they were when dinosaurs still walked the Earth. The isolation is not merely spatial but temporal, a disconnection from the contemporary universe that grows more profound with distance. These lonely galaxies will become lonelier still. Cosmic expansion continues to stretch the voids, carrying their sparse populations of galaxies farther apart. In 100 billion years, a galaxy in a void center may find its nearest neighbor receding at velocities approaching the speed of light. Its light red-shifted beyond detection, its existence erased from the observable universe of the void dweller. The isolation that currently characterizes these systems represents merely an early stage of a process that will eventually affect all galaxies everywhere, as expansion carries every system beyond the cosmic horizon of every other. But even as cosmic expansion carries distant objects beyond our reach, the universe itself provides tools for seeing what should otherwise remain hidden. Gravity, the same force that binds galaxies into clusters and clusters into superclusters, also bends the fabric of space-time in ways that turn massive objects into cosmic magnifying glasses. This phenomenon, gravitational lensing, allows astronomers to peer deeper into the universe than their telescopes alone could ever achieve, revealing galaxies and structures that would otherwise remain invisible against the darkness. The physics underlying this effect emerges directly from Einstein's general theory of relativity, published in 1915. Mass does not merely attract other masses through some invisible force acting across empty space. Instead, mass curves the geometry of space-time itself, and objects moving through that curved geometry follow paths that appear bent when viewed from a distance. Light, despite having no rest mass, must also follow these curved paths. A photon traveling through the universe traces what physicists call a geodesic, the straightest possible line through curved space-time. When that space-time is warped by a massive object, the straightest possible line becomes curved from the perspective of a distant observer. The first confirmation of this effect came during the solar eclipse of May 29, 1919, when Arthur Eddington led expeditions to Príncipe Island off the coast of Africa and to Sobral in Brazil. During the few minutes of totality, when the moon blocked the sun's blinding disk, astronomers photographed stars whose light passed close to the solar limb. The positions of those stars appeared shifted by approximately 1.75 arc-seconds compared to their positions when the sun was elsewhere in the sky. This deflection matched Einstein's predictions precisely, confirming that the sun's mass was bending starlight. The sun, with its mass of 2 × 10⁻30 kilograms, was acting as a lens, albeit a weak one. but the Sun represents a trivial mass compared to the objects that produce the most dramatic lensing effects in the cosmos. Galaxy clusters, containing hundreds or thousands of individual galaxies bound together by gravity, possess total masses ranging from 10 to the power of 14 to 10 to the power of 15 solar masses. These enormous concentrations of matter create gravitational fields so intense that they bend light from background objects through angles of several arc-seconds, producing visible distortions that transform distant galaxies into arcs, rings, and multiple images. The geometry of gravitational lensing depends on the precise alignment between the observer, the lensing mass, and the background source. When alignment is perfect, with the source lying directly behind the lens as seen from Earth, the background object's light is bent equally in all directions, producing a complete ring of light surrounding the foreground mass. These structures, called Einstein rings, represent the most symmetric manifestation of gravitational lensing. The first complete Einstein ring was discovered in 1988, a radio source designated MG1131+0456, where a distant quasar's radio emission was bent into a nearly perfect circle by an intervening galaxy. More commonly, alignment is imperfect, and the lensing produces arcs rather than complete rings. The Abell 370 galaxy cluster, located approximately 4 billion light-years from Earth in the constellation Cetus, provides one of the most spectacular examples. Behind this cluster lies a galaxy at a redshift of Z equals 0.725, corresponding to a distance of approximately 6 billion light-years. The cluster's gravitational field has stretched this background galaxy into a luminous arc, spanning nearly 30 arc-seconds across the sky, an object so distorted that early observers mistook it for an unusual feature of the cluster itself rather than a background object. The magnification provided by gravitational lensing follows directly from the geometry of light bending. When a massive object focuses light from a background source, it effectively increases the solid angle over which that source's light reaches the observer. This magnification can be substantial. In the case of the galaxy cluster MAX J0416.1-2403, located 4.3 billion light-years away, background galaxies are magnified by factors of 10 to 100, making objects visible that would otherwise fall below the detection threshold of even the most powerful telescopes. This magnification has proven essential for studying the earliest galaxies in the universe. The galaxy designated MAX 0647-JD was discovered in 2012 through the gravitational lensing provided by the cluster MAX J0647.7+7015. Without lensing, this galaxy, lying at a redshift of Z equals 10.7 and a look-back time of 13.3 billion years, would have been too faint to detect. The cluster's gravitational field magnified its light by a factor of approximately 8, bringing it within reach of the Hubble Space Telescope's instruments. The galaxy appears as 3 separate images, each corresponding to light, that took a different path around the lensing cluster, bent by different amounts depending on its trajectory through the curved space-time. The multiple images produced by gravitational lensing carry information beyond mere positions. Because light following different paths around a lensing mass travels different distances, the images arrive at Earth at different times. For a strongly lensed quasar, where the background object varies in brightness over days or weeks, astronomers can measure these time delays directly. The quasar S DSSJ 1004 + 4112, lensed by a foreground galaxy cluster, produces 5 distinct images with time delays ranging from 40 to 822 days between them. These delays depend on the mass distribution of the lens and the geometry of the universe itself, providing an independent method for measuring the Hubble constant, the rate at which the universe expands. Current measurements using time delay cosmography yield Hubble constant values of approximately 73 kilometers per second per megaparsec, consistent with local distance ladder measurements, but in tension with values derived from the cosmic microwave background. This discrepancy, known as the Hubble tension, represents one of the most significant puzzles in modern cosmology, and gravitational lensing provides one of the few methods capable of addressing it independently. Beyond strong lensing, where images are visibly distorted into arcs and rings, a subtler effect pervades the entire sky. Weak gravitational lensing produces distortions too small to detect in individual galaxies, but statistically measurable across large populations. Every galaxy image we observe has been slightly stretched and sheared by the cumulative gravitational influence of all the mass between that galaxy and Earth. By measuring the correlations in these tiny distortions across millions of galaxies, astronomers can map the distribution of matter in the universe, including the dark matter that produces no light of its own. The Dark Energy Survey, observing from the Cerro Tololo Inter-American Observatory in Chile, has measured weak lensing signals from over 100 million galaxies, creating maps of dark matter distribution spanning billions of light years. These maps reveal the cosmic web in its full three-dimensional structure, showing how matter clusters along filaments and around nodes while leaving the great voids nearly empty. The weak lensing signal from a typical background galaxy corresponds to a distortion of only about 2% in its ellipticity, a change far smaller than the intrinsic variation in galaxy shapes. Only by averaging over vast numbers of galaxies does the coherent lensing signal emerge from the noise. Gravitational lensing also reveals objects that emit no light at all. When a compact, massive object passes between Earth and a background star, the star's light is bent around the intervening mass, temporarily brightening as the alignment improves, and then fading as the lens moves on. This microlensing effect has been used to detect planets orbiting distant stars, brown dwarfs too dim to see directly, and isolated black holes wandering through the galaxy. In 2022, astronomers announced the detection of a stellar mass black hole approximately 5,000 light-years from Earth, identified solely through its gravitational lensing of a more distant star. The black hole, with a mass of approximately 7 solar masses, produced a brightening event lasting over 200 days as it drifted across the line of sight. The most extreme gravitational lenses in the universe are the supermassive black holes at the centers of galaxies. These objects, with masses ranging from millions to billions of solar masses, curve spacetime so severely that light can orbit them multiple times before escaping. The black hole at the center of the galaxy M87 imaged by the Event Horizon Telescope in 2019, has a mass of 6.5 billion solar masses and an event horizon spanning approximately 38 billion kilometers. Light passing close to this horizon is bent through angles of 180 degrees or more, creating the distinctive shadow surrounded by a bright ring of emission that the telescope captured. Through gravitational lensing, the universe reveals what would otherwise remain hidden. Galaxies too distant and too faint to detect directly become visible when magnified by foreground clusters. The distribution of invisible dark matter becomes mappable through its subtle distortion of background light. Objects that emit no radiation at all betray their presence through the bending of space-time around them. In a cosmos where expansion carries ever more objects beyond our observational horizon, gravitational lensing provides a tool for extending our reach, using the mass of the universe itself as a telescope of cosmic proportions. Among the most luminous objects that gravitational lensing helps reveal are quasars, cosmic beacons so bright they outshine entire galaxies despite originating from regions smaller than our solar system. These extraordinary sources of radiation mark the locations of supermassive black holes actively consuming matter at prodigious rates, converting the gravitational energy of infalling gas into light with efficiencies that dwarf any other known process in the universe. The most distant quasars discovered to date shine from epochs when the universe was less than 1 billion years old, their light having traveled for more than 13 billion years to reach our telescopes. The physics that makes quasars visible across such immense distances begins with accretion, the process by which matter spirals inward toward a black hole. Gas falling toward a supermassive black hole does not plunge directly into the event horizon. Instead, conservation of angular momentum forces it into a flattened disk, a swirling structure where friction between adjacent layers heats the material to extraordinary temperatures. In the innermost regions of these accretion disks, where gas orbits at significant fractions of the speed of light, temperatures exceed millions of degrees Kelvin. Matter at these temperatures radiates across the electromagnetic spectrum, from radio waves through infrared and visible light to ultraviolet and X-rays. The luminosity of a quasar depends primarily on the rate at which matter falls into its central black hole. A supermassive black hole consuming material at the Eddington limit, the theoretical maximum rate at which radiation pressure from the infalling matter balances gravitational attraction, can convert roughly 10% of the rest mass energy of that material into radiation. This efficiency far exceeds nuclear fusion, which converts less than 1% of hydrogen's mass into energy. A quasar powered by a black hole of 1 billion solar masses accreting at the Eddington rate would shine with a luminosity of approximately 10 to the 47th ergs per second, equivalent to roughly 1 trillion suns, all emanating from a region smaller than the distance from the Sun to Neptune. The most distant quasar currently confirmed, designated J0313-1806, lies at a redshift of Z equals 7.64, meaning the light we observe from it departed when the universe was only 670 million years old. This quasar harbors a supermassive black hole with a mass of approximately 1.6 billion solar masses, a staggering amount of matter to have accumulated in such a brief cosmic interval. The existence of such massive black holes so early in cosmic history poses significant challenges to our understanding of black hole formation and growth. Standard models of stellar evolution and black hole accretion struggle to explain how objects this massive could have formed in the time available. Several mechanisms have been proposed to account for these early supermassive black holes. Direct collapse scenarios suggest that in the early universe, pristine gas clouds lacking the heavy elements that promote fragmentation could have collapsed directly into black holes with masses of 10,000 to 100,000 solar masses, providing a substantial head start for subsequent growth. Alternatively, the first generation of stars, forming from pure hydrogen and helium, may have been far more massive than stars forming today, potentially reaching several hundred solar masses before exploding or collapsing into black holes that served as seeds for later growth. Some models invoke periods of super-Eddington accretion, where black holes temporarily consumed matter faster than the theoretical limit through geometries that allowed radiation to escape without impeding the infall of additional material. The quasar ULAS J1342+0928, discovered in 2017, holds a redshift of Z equals 7.54, placing it at a look-back time of 13.1 billion years. The black hole at its center contains approximately 800 million solar masses, and the quasar shines with a bolometric luminosity of 4 × 10 to the 47th ergs per second. Observations of this object reveal not only the quasar itself, but also the galaxy hosting it, a system actively forming stars at a rate of approximately 100 solar masses per year. The interstellar medium of this host galaxy shows evidence of heavy elements, indicating that multiple generations of stars had already lived and died by this early epoch, enriching the gas with carbon, oxygen, and other products of stellar nucleosynthesis. Even more distant quasar candidates continue to emerge from deep surveys. The object designated J0439+1634 at redshift Z equals 6.52 benefits from gravitational lensing by a foreground galaxy, which magnifies its apparent brightness by a factor of approximately 50. Without this cosmic magnification, the quasar would be too faint for detailed spectroscopic study. The lensing allows astronomers to examine the chemical composition of gas along the line of sight, revealing the presence of ionized carbon, silicon, and magnesium in the intergalactic medium at this early epoch. The spectra of distant quasars carry information not only about the quasars themselves, but also about all the matter their light has traversed during its journey to Earth. Absorption features in quasar spectra reveal the presence of intervening gas clouds, galaxies, and the diffuse intergalactic medium. The Lyman alpha forest, a series of absorption lines caused by neutral hydrogen along the line of sight, becomes increasingly dense at higher redshifts, eventually merging into a continuous absorption trough called the Gunn-Peterson trough. This trough indicates that the intergalactic medium was substantially neutral at redshifts above approximately 6, marking the epoch before cosmic reionization was complete. Quasars themselves played a crucial role in reionization. the process by which the neutral hydrogen that filled the universe after recombination was ionized by ultraviolet radiation from the first luminous sources. The intense ultraviolet output of early quasars carved out ionized bubbles in the surrounding neutral medium, regions where hydrogen atoms had been stripped of their electrons. These bubbles grew and eventually merged as more sources of ionizing radiation appeared, completing the transformation of the intergalactic medium from opaque to transparent by approximately 1 billion years after the Big Bang. The search for ever more distant quasars continues with each generation of telescopes. The James Webb Space Telescope, with its unprecedented sensitivity in the infrared, can detect quasars at redshifts where their light has been shifted entirely out of the visible spectrum. At redshift z equals 10, the Lyman alpha emission line, which in the rest frame lies at 121.6 nanometers in the ultraviolet, appears at 1.34 micrometers in the near infrared. At redshift z equals 15, this same line would appear at 1.94 micrometers. The infrared capabilities of modern instruments open windows to epochs ever closer to the formation of the first luminous objects. The farthest quasars serve as more than mere distance markers. They function as cosmic laboratories, allowing astronomers to study the physics of accretion, the growth of supermassive black holes, the chemical enrichment of the early universe, and the process of reionization. Each photon arriving from these distant beacons carries information encoded during its emission more than 13 billion years ago, preserved through its journey across an expanding universe. In the light of the most distant quasars, we observe the universe as it existed when the first massive structures were assembling, when supermassive black holes were growing at rates that challenge our theoretical understanding, and when the cosmos was transitioning from its dark ages into the era of galaxies and stars that continues to the present day. Yet quasars, for all their brilliance, are not the most energetic signals the universe sends across cosmological distances. Occasionally, the cosmos produces events so violent, so concentrated in their energy release, that they briefly outshine everything else in the observable universe. These are gamma-ray bursts, the most powerful explosions known to physics, and their detection from billions of light-years away provides glimpses of cataclysmic processes occurring when the universe was young. A gamma-ray burst releases more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. The most energetic examples, known as long-duration gamma-ray bursts, can output approximately 10 to the power of 47 joules in less than a minute, a figure so extreme that it challenges intuitive comprehension. If such an event occurred within a few thousand light-years of Earth, the radiation would strip away the ozone layer and trigger mass extinction. Yet because these bursts originate at cosmological distances, typically billions of light-years away, they arrive as faint signals detectable only by specialized satellites orbiting above Earth's atmosphere. The physics underlying long-duration gamma-ray bursts involves the death of massive stars, but deaths far more violent than ordinary supernovae. When a star exceeding approximately 25 solar masses exhausts its nuclear fuel, its core collapses not into a neutron star but directly into a black hole. The surrounding stellar material, still falling inward at velocities approaching the speed of light, forms an accretion disk around the newborn black hole. Jets of matter and radiation punch outward along the rotational axis at 99.99% of light speed, producing relativistic beams of gamma radiation. These jets, narrowly focused like cosmic searchlights, carry the concentrated energy of stellar collapse across the universe. The most distant gamma-ray burst ever detected, designated GRB 090423, occurred at a redshift of Z=8.2, corresponding to a look-back time of approximately 13.1 billion years. When this burst occurred, the universe was only 630 million years old, less than 5% of its current age. The light from this explosion traveled across an expanding cosmos for over 13 billion years before triggering detectors aboard the Swift satellite in April 2009. For approximately 10 seconds, the dying star briefly became the most distant object ever observed by humanity, its death cry crossing almost the entire observable universe. Another remarkable example, GRB 090429b, may have originated at an even greater distance, with preliminary estimates suggesting a red shift near Z=9.4, though spectroscopic confirmation remains uncertain. If accurate, this would place the burst at a look-back time of 13.2 billion years, when the universe was approximately 520 million years old. At such distances, gamma-ray bursts serve as probes of the early universe, their afterglows illuminating the intergalactic medium through which their light traveled, and revealing the chemical composition of gas clouds that existed before most galaxies had formed. The detection of gamma-ray bursts from such extreme distances relies on their extraordinary luminosity and the transparency of the universe to gamma radiation. Unlike visible light, which can be absorbed by dust and gas, gamma rays penetrate most intervening material. However, the expansion of the universe redshifts even gamma rays, stretching their wavelengths as they travel. A burst emitted primarily in gamma rays arrives at Earth with its spectrum shifted into X-rays, ultraviolet, and eventually visible and infrared wavelengths. The afterglow of GRB 090423, for example, was detected primarily in infrared light, its original gamma radiation having been stretched by a factor of 9.2 during its 13.1 billion-year journey. Short-duration gamma-ray bursts lasting less than 2 seconds arise from a different mechanism entirely. These events occur when two neutron stars spiral together and merge, or when a neutron star falls into a black hole. The collision of two neutron stars, each containing approximately 1.4 solar masses, compressed into spheres roughly 20 kilometers in diameter, releases gravitational binding energy equivalent to several percent of the total mass, converted directly into radiation. The merger event GW 170817, detected in August 2017, at a distance of approximately 130 million light-years, produced both gravitational waves and a short gamma-ray burst, confirming the connection between neutron star mergers and these brief but intense explosions. The energy budget of gamma-ray bursts reveals the extremity of the physics involved. A typical long-duration burst releases approximately 10 to the power of 44 joules in gamma radiation alone, with additional energy carried away by neutrinos, gravitational waves, and the kinetic energy of the expanding debris. The jets themselves move at Lorentz factors of several hundred, meaning time dilation effects compress what might be minutes of emission in the source frame into seconds as observed from Earth. The temperature within the jet reaches billions of Kelvin, hot enough that matter exists as a plasma of electrons, positrons, and photons in thermal equilibrium. The afterglow phase of a gamma-ray burst, lasting hours to weeks after the initial flash, provides crucial information about the burst environment and distance. As the relativistic jet decelerates by sweeping up surrounding material, it produces synchrotron radiation across the electromagnetic spectrum. Observations of this afterglow in X-ray, optical, and radio wavelengths allow astronomers to measure the redshift of the host galaxy, determine the energy of the explosion, and study the properties of the circumburst medium. For the most distant bursts, the afterglow may be the only means of confirming the cosmological distance, as the host galaxies themselves are often too faint to detect. Gamma-ray bursts occurring at high redshift probe the epoch of reionization, the period when ultraviolet radiation from the first stars and galaxies ionized the neutral hydrogen that filled the universe after recombination. The spectrum of a distant burst's afterglow carries absorption features imprinted by intervening gas clouds, revealing the ionization state of the intergalactic medium along the line of sight. Observations of GRB 050904 at redshift Z equals 6.3 showed that the universe was still partially neutral at that epoch, with approximately 10% of hydrogen remaining in atomic form. Such measurements complement quasar observations in mapping the progress of reionization across cosmic time. The rate of gamma-ray bursts appears to have been higher in the early universe, correlating with the elevated star formation rate during the first few billion years after the Big Bang. Current estimates suggest that a gamma-ray burst occurs somewhere in the observable universe, approximately once per day, though only a fraction of these are oriented such that their jets point toward Earth. The beaming angle of a typical long-duration burst spans roughly 5 degrees, meaning that for every burst we detect, approximately 100 occur with jets pointed in other directions, invisible to our instruments. Detection of these distant cataclysms requires satellites positioned above Earth's atmosphere, which absorbs gamma radiation before it reaches the surface. The SWIFT satellite, launched in 2004, carries instruments capable of detecting a burst, determining its position within arc minutes, and slewing its X-ray and optical telescopes to observe the afterglow within seconds. The Fermi Gamma Ray Space Telescope, operational since 2008, monitors the entire sky visible from its orbit, detecting approximately 200 bursts per year. Together, these observatories have catalogued thousands of gamma-ray bursts, with distances ranging from a few hundred million light-years to the edge of the observable universe. Each gamma-ray burst represents a singular event, a massive star's final moments, or the merger of compact objects that had orbited each other for billions of years. The photons arriving at Earth from the most distant bursts have traveled for over 13 billion years, crossing voids between galaxy clusters, passing through the gravitational lenses of intervening mass concentrations and red-shifting steadily as space itself expanded. In detecting these signals, we observe the deaths of stars that existed before the Milky Way had formed, explosions that occurred when the universe was emerging from its dark ages into the era of cosmic structure we inhabit today. Beyond even the most distant gamma-ray bursts, beyond the farthest quasars and the earliest galaxies our telescopes have captured, there exists a boundary that no electromagnetic observation can penetrate. This is not a physical wall, not a structure made of matter, but rather a surface defined by the physics of the early universe itself. The cosmic microwave background radiation represents the oldest light we will ever detect. Photons released approximately 380,000 years after the Big Bang, now arriving at Earth from every direction in the sky after a journey spanning 13.8 billion years. To understand why this radiation marks an absolute limit to our observations, we must consider the conditions that prevailed in the young universe. In the first moments after the Big Bang, temperatures exceeded 10 billion Kelvin, far too hot for atoms to exist. Matter consisted of a plasma, a dense soup of free electrons, protons, and neutrons, along with enormous quantities of photons. In this state, light could not travel freely. Photons scattered constantly off free electrons through a process called Thomson scattering, bouncing from particle to particle like light diffusing through thick fog. The universe was opaque, filled with energy but impenetrable to observation. As the cosmos expanded, it cooled. The temperature dropped according to a precise relationship with the scale factor of the universe, decreasing roughly in inverse proportion to how much space had stretched. When the universe reached an age of approximately 380,000 years, the temperature had fallen to around 3,000 Kelvin, roughly the surface temperature of a cool red star. At this threshold, something remarkable occurred. Electrons, which had been moving too fast to be captured by atomic nuclei, finally slowed enough to combine with protons and form neutral hydrogen atoms. This transition, called recombination despite the fact that electrons and protons had never been combined before, fundamentally changed the optical properties of the universe. Neutral hydrogen does not scatter photons in the same way free electrons do. Once recombination occurred, the fog lifted. Photons that had been trapped in endless scattering suddenly found themselves free to travel unimpeded through space. They began their journey across the cosmos, carrying with them information about the conditions at the moment of their release. The surface from which these photons last scattered is called the surface of last scattering, and it surrounds us in every direction at a distance defined not by space alone, but by the expansion history of the universe. The cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories in New Jersey. They were calibrating a horn antenna designed for satellite communication when they encountered persistent noise they could not eliminate. This noise came uniformly from all directions and corresponded to radiation with a temperature of approximately 3 Kelvin. What they had discovered, initially to their puzzlement, was the afterglow of the Big Bang itself, the remnant radiation from the moment the universe became transparent. The original photons released at recombination had a temperature of about 3000 Kelvin, corresponding to visible light with an orange-red glow. If we could have witnessed the universe at that moment, the sky would have appeared uniformly bright, like being inside a cooling furnace. But those photons have been traveling for 13.8 billion years through an expanding universe. As space stretched, the wavelengths of these photons stretched with it, a phenomenon called cosmological redshift. Light that began as visible radiation has now been stretched into the microwave portion of the electromagnetic spectrum, with wavelengths measured in millimeters rather than nanometers. The redshift of the cosmic microwave background is approximately z equals 1100. This number means that the wavelengths of CMB photons have been stretched by a factor of about 1100 since their emission. It also means that the universe has expanded by that same factor since recombination. When these photons began their journey, the observable universe was roughly 1,100 times smaller than it is today, compressed into a volume where the average density of matter was over 1 billion times higher than the current cosmic average. Modern measurements of the cosmic microwave background have achieved extraordinary precision. The Planck satellite, operated by the European Space Agency from 2009 to 2013, mapped the CMB with angular resolution of about 5 arc-minutes and temperature sensitivity of millionths of a degree. These observations revealed that the CMB has a temperature of 2.7255 Kelvin, uniform across the sky, to better than 1 part in 100,000. This uniformity presents both a triumph and a puzzle for cosmology. The uniformity confirms that the early universe was remarkably homogeneous, but it also raises questions about how regions that were never in causal contact could have reached the same temperature. Within this near-perfect uniformity lie tiny fluctuations, variations in temperature of roughly 18 microkelvins from the average. These fluctuations, visible in CMB maps as slightly warmer and cooler patches, represent the seeds of all cosmic structure. Regions that were slightly denser than average at the time of recombination had slightly higher temperatures. These overdense regions would later collapse under gravity to form the first galaxies, galaxy clusters, and the cosmic web of filaments and voids we observe today. Every galaxy, every star, every planet traces its origin to quantum fluctuations that were imprinted on the CMB 380,000 years after the Big Bang. The surface of last scattering is not located at a single distance from Earth, because light travels at a finite speed, and the universe has been expanding throughout the journey of CMB photons. The proper distance to this surface is approximately 46 billion light-years. This number exceeds the age of the universe multiplied by the speed of light, because space itself has expanded while the photons were in transit. The light travel time, however, is 13.8 billion years minus 380,000 years, essentially the entire age of the cosmos. When we observe the cosmic microwave background, we are looking back to an epoch when the universe was less than 0.003% of its current age. Beyond the surface of last scattering, electromagnetic observation becomes impossible. The universe before recombination was opaque, and no photons from that era survive to reach our detectors. This creates a fundamental observational horizon, a curtain drawn across the earliest moments of cosmic history. We can infer what conditions were like before recombination through theoretical models and through observations of phenomena like the abundance of light elements, which were forged in the first few minutes after the Big Bang. But we cannot see those epochs directly using light. The cosmic microwave background fills the universe with approximately 411 photons per cubic centimeter. These ancient photons vastly outnumber the atoms in the cosmos, with roughly 2 billion cmb photons for every baryon. They carry a total energy density that, while small compared to matter today, dominated the energy content of the universe for the first 47,000 years after the Big Bang. Even now, the CMB contributes to the overall energy budget of the cosmos, a faint but omnipresent reminder of the hot, dense state from which everything emerged. The patterns in the cosmic microwave background encode information about fundamental cosmological parameters. The angular size of the temperature fluctuations reveals the geometry of the universe, indicating that space is flat to within a fraction of a percent. The relative heights of peaks in the CMB power spectrum constrain the density of ordinary matter, dark matter, and dark energy. From these observations, cosmologists have determined that ordinary atoms constitute only about 5% of the total energy density of the universe, with dark matter contributing 27% and dark energy comprising the remaining 68%. As we observe the cosmic microwave background, we are witnessing the universe at its youngest visible age, a moment frozen in time and stretched across the sky. The photons arriving at our detectors tonight left the surface of last scattering when the cosmos was a nearly uniform plasma, before any stars had formed, before any galaxies existed, before the first heavy elements had been forged in stellar cores. They have traveled through the entire history of cosmic structure formation, passing by objects that would not exist for billions of years after their journey began. In detecting this radiation, we touch the boundary of the observable, the edge beyond which light itself cannot carry information to our instruments. Yet even as the cosmic microwave background represents the oldest light we can detect, it is not the oldest moment in cosmic history. Behind that wall of ancient photons lies an era we cannot observe with electromagnetic radiation, a period when the universe existed in a state fundamentally hostile to the transmission of light. For approximately 380,000 years after the Big Bang, the cosmos remained opaque, a dense plasma where photons could not travel freely, where every particle of light was trapped in an endless series of collisions with free electrons. This epoch, known as the plasma era or the photon epoch, contains information forever locked away from our telescopes, hidden behind the surface of last scattering like words, written on pages that were burned before anyone could read them. To understand why this period remains invisible, we must examine the physics of plasma and the behavior of light within it. In the earliest moments after the Big Bang, temperatures exceeded 10 billion Kelvin, far too hot for atoms to exist in any stable form. Protons and neutrons moved freely, colliding with tremendous energy, while electrons existed as an independent population of charged particles. Photons, the carriers of electromagnetic force, and the medium through which we observe the universe, could not travel more than a fraction of a second before encountering a free electron and scattering in a random direction. The mean free path of a photon during this era, the average distance light could travel before being deflected, was extraordinarily short compared to the scale of the universe itself. This scattering process, known as Thomson scattering, occurs when photons interact with free electrons. The cross-section for this interaction, approximately 6.65 times 10 to the negative 29 square meters, might seem vanishingly small, but when multiplied by the enormous density of free electrons in the early universe, it created an environment where light was effectively imprisoned. A photon emitted at any point in this plasma would scatter within microseconds, changing direction randomly, carrying no coherent information about its origin. The universe during this epoch was like a fog so thick that visibility extended only centimeters, except the fog was made of charged particles, and the visibility was measured in fractions of cosmic time. As the universe expanded, it cooled according to the relationship between temperature and scale factor. The temperature dropped proportionally to the inverse of the expansion, meaning that as the cosmos doubled in size, its temperature halved. At approximately 380,000 years after the Big Bang, the temperature had fallen to roughly 3,000 Kelvin, cool enough for electrons to combine with protons and form neutral hydrogen atoms in a process called recombination. This transition did not happen instantaneously, but occurred over a period of roughly 100,000 years, as the probability of electron capture gradually exceeded the probability of ionization by ambient photons. Once hydrogen atoms formed, the universe became transparent almost immediately in cosmic terms. Neutral hydrogen does not scatter visible light efficiently because its electrons are bound in specific energy levels, unable to interact with photons that do not match precise transition energies. The mean free path of photons suddenly increased from microscopic scales to distances larger than the observable universe. Light was released, free to travel across billions of light years and billions of years, eventually reaching our detectors as the cosmic microwave background. But the photons that existed before recombination, the light that was trapped in the plasma, carries no information we can recover. Each scattering event randomized the direction and effectively erased any memory of previous interactions. The plasma era itself contained several distinct phases, each with its own physics and its own secrets hidden from our view. In the first second after the Big Bang, temperatures exceeded 10 billion Kelvin, and the universe contained a soup of quarks, gluons, electrons, positrons, neutrinos, and photons in thermal equilibrium. As temperatures dropped below approximately 1 trillion Kelvin, quarks combined to form protons and neutrons in a process called hadronization. This transition, occurring roughly 1 microsecond after the Big Bang, fundamentally changed the composition of matter, but left no direct electromagnetic signature we can observe. Between approximately 1 second and 3 minutes after the Big Bang, the universe underwent Big Bang nucleosynthesis, the formation of the first atomic nuclei. At temperatures between 1 billion and 100 million Kelvin, protons and neutrons fused to create deuterium, helium-3, helium-4, and trace amounts of lithium-7. This process determined the primordial abundances of light elements, with roughly 75% hydrogen and 25% helium by mass, plus tiny fractions of heavier isotopes. We can infer this nucleosynthesis occurred by measuring element abundances in ancient, chemically primitive stars, but we cannot observe the process directly. The photons present during nucleosynthesis were scattered countless times before recombination. Their information about this era thoroughly scrambled. The period between nucleosynthesis and recombination, spanning from 3 minutes to 380,000 years, represents the longest continuous epoch we cannot observe electromagnetically. During this time, the universe consisted primarily of hydrogen and helium nuclei, free electrons, photons, and dark matter. The photons and matter existed in thermal equilibrium, constantly exchanging energy through scattering, maintaining a nearly perfect blackbody spectrum. Small density fluctuations, seeded by quantum variations during cosmic inflation, began to grow under the influence of gravity. But the pressure of the photon-baryon fluid prevented matter from collapsing into structures. These acoustic oscillations, sound waves propagating through the plasma at roughly 57% of the speed of light, left their imprint on the cosmic microwave background as the characteristic pattern of hot and cold spots we observe today. Yet the oscillations themselves, the actual sound waves moving through the early universe, remain invisible. We see only their frozen aftermath, the pattern they created at the moment of recombination, like seeing the ripples on a pond surface without witnessing the stone that caused them. The physics of these oscillations is well understood, governed by the interplay between gravitational attraction pulling matter together and radiation pressure pushing it apart. The fundamental mode of oscillation, the largest wave that had time to complete one compression before recombination, corresponds to an angular scale of approximately 1 degree on the sky, a feature prominently visible in cosmic microwave background maps. Higher harmonics, smaller scale oscillations that completed multiple cycles, create the detailed peak structure in the CMB power spectrum that allows cosmologists to measure cosmic parameters with remarkable precision. Information from before the plasma era is even more thoroughly hidden. The epoch of cosmic inflation, believed to have occurred within the first fraction of a second after the Big Bang, expanded the universe by a factor of at least 10 to the 26th in a time interval shorter than 10 to the negative 32 seconds. This exponential expansion stretched quantum fluctuations to cosmic scales, seeding the density variations that would eventually become galaxies and galaxy clusters. But inflation occurred at energies and temperatures so extreme that no electromagnetic radiation from this period could survive. The only potential observational window into inflation comes from gravitational waves, ripples in space-time itself that would not have been scattered by the plasma, and could theoretically be detected through their imprint on the polarization of the cosmic microwave background. The search for these primordial gravitational waves represents one of the most challenging frontiers in observational cosmology. If inflation generated gravitational waves of sufficient amplitude, they would have left a distinctive swirling pattern called B-mode polarization in the cosmic microwave background. Experiments like BICEP and the Keck array have searched for this signal, achieving sensitivities capable of detecting gravitational wave amplitudes at the level of a few parts in 10 million of the cmb temperature. So far, confirmed detections remain elusive, constrained by foreground contamination from dust in our own galaxy, and by the fundamental weakness of the expected signal. The universe before recombination guards its secrets well. And so the cosmic microwave background marks not the edge of existence, but the edge of visibility. Beyond that ancient wall of light, the universe continues in all directions, filled with matter and energy and structure that we will never observe directly. This distinction between what we can see and what actually exists represents one of the most profound limitations in all of science, a boundary imposed not by our technology, but by the fundamental nature of light, time, and cosmic expansion. The observable universe forms a sphere centered on Earth, not because our planet occupies any special position, but because we are the observers. Every point in the cosmos has its own observable universe, its own sphere of visibility determined by how far light has traveled since the Big Bang. From our vantage point, this sphere extends approximately 46.5 billion light-years in every direction, a radius that seems paradoxical given that the universe is only 13.8 billion years old. The resolution to this apparent contradiction lies in cosmic expansion. Light that left distant regions billions of years ago has been traveling toward us, even as the space between us and those regions stretched. The photons we receive today from the cosmic microwave background began their journey from matter that was only about 42 million light-years away at the moment of emission. But during the 13.8 billion years those photons spent crossing space, expansion carried that matter outward. Today, the regions that emitted the CMB we observe lie approximately 46 billion light-years distant, receding from us at velocities exceeding the speed of light. This creates the observable universe's defining characteristic. It is a sphere of past light, not present reality. When we observe a galaxy at a distance of 10 billion light-years, we see it as it existed 10 billion years ago. That galaxy has continued evolving, forming new stars, merging with neighbors, perhaps being consumed by a larger structure. Its present state remains unknown to us, and depending on its recession velocity, its present state may remain forever unknowable. The observable universe is thus a temporal cross-section, a view that samples different cosmic epochs at different distances. Nearby galaxies appear as they were millions of years ago. Distant galaxies appear as they were billions of years ago. The cosmic microwave background appears as the universe was 380,000 years after the Big Bang. We see not a snapshot of the cosmos, but a nested series of historical shells, each more ancient than the last. The particle horizon defines the absolute outer boundary of this observable sphere. It marks the maximum distance from which any signal, traveling at the speed of light since the beginning of time, could have reached us by now. Beyond this horizon, no causal connection has ever been possible. Light from regions beyond the particle horizon has simply not had enough time to arrive, regardless of how fast it traveled or when it began its journey. The particle horizon currently lies at a comoving distance of approximately 46.9 billion light-years, slightly larger than the distance to the surface of last scattering, because the horizon accounts for all possible signals, not just the CMB photons that happened to reach us from that particular epoch. But the particle horizon is not static. It expands as the universe ages, growing at the speed of light in proper distance terms. Though cosmic expansion complicates this simple picture, every second that passes allows light from slightly more distant regions to reach us for the first time. In principle, our observable universe grows continuously, incorporating new volumes of space into our cosmic sphere of visibility. Yet this growth competes against accelerating expansion. Regions that lie just beyond our current horizon are receding so rapidly that their light, despite traveling toward us at 299,792 kilometers per second, loses ground against the stretching of intervening space. The light approaches, but the distance it must cross grows faster than it can traverse. This competition between light propagation and cosmic expansion defines the event horizon, a second boundary distinct from the particle horizon. The event horizon marks the maximum distance from which light emitted today could ever reach us, given infinite time. Because expansion is accelerating under the influence of dark energy, the event horizon is shrinking in co-moving coordinates. Regions that we could theoretically receive signals from in a decelerating universe will never send us detectable light in our accelerating one. The current cosmic event horizon lies at approximately 16 billion light-years in co-moving distance. Any galaxy currently beyond this radius, even if it emits light directly toward us at this very moment, will never have that light reach Earth. The expansion of space will stretch those photons, redshift them toward infinite wavelengths, and carry them away faster than they can approach. The actual universe, in contrast to the observable universe, has no known boundary. Cosmological observations suggest that space extends far beyond our horizon, filled with galaxies and clusters and voids that mirror the structures we observe locally. The cosmic microwave background provides our strongest evidence for this extrapolation. Its uniformity implies that the early universe was homogeneous on scales much larger than our observable patch. The slight temperature variations we detect, at the level of 1 part in 100,000, follow statistical patterns consistent with random quantum fluctuations stretched across all of space, not just the portion we can see. If the universe were significantly different beyond our horizon, if it contained vast empty regions or dramatically different densities, we would expect to see asymmetries in the CMB that we do not observe. Inflationary cosmology suggests the actual universe may be incomprehensibly larger than the observable portion. During inflation, space expanded by a factor of at least 10 to the 26th power in a fraction of a second, taking a region smaller than a proton and stretching it to scales far exceeding our current horizon. If inflation lasted even slightly longer than the minimum required to explain observed flatness and homogeneity, the universe could be billions of times larger than the observable sphere. Some inflationary models predict a universe so vast that the observable portion represents a ratio comparable to a single atom relative to the entire Earth. We would be seeing an infinitesimally small sample of a cosmos that extends, for all practical purposes, forever. The geometry of space provides additional constraints on the actual universe's extent. Measurements of the cosmic microwave background, particularly by the Planck satellite, indicate that space is flat to within 0.4% uncertainty. A perfectly flat universe, one where parallel lines remain parallel forever, and the angles of a triangle sum to exactly 180 degrees, can be either infinite or finite depending on its topology. An infinite, flat universe extends without boundary in all directions. A finite, flat universe could curve back on itself like the surface of a torus, creating a space that is boundaryless but limited in volume. Current observations cannot distinguish between these possibilities because any topological curvature would only become apparent on scales larger than our observable horizon. The distinction between observable and actual carries profound implications for cosmology. Every measurement we make, every theory we test, every conclusion we draw about the universe applies with certainty only to the observable portion. We assume, based on the Copernican principle, that our location is not special, that the universe looks roughly the same from every vantage point. This assumption has been validated on every scale we can test, from the distribution of galaxies to the uniformity of the CMB. But it remains an assumption when applied beyond the horizon. The actual universe could contain regions with different physical constants, different vacuum energies, different outcomes of symmetry breaking in the early cosmos. We would have no way of knowing. This limitation extends to fundamental questions about cosmic structure. We observe that the universe is expanding, that galaxies are receding from each other, that space itself is stretching. But we observe this only within our horizon. The actual universe could contain regions where expansion has reversed, where gravity has overcome dark energy, where matter has collapsed into structures we cannot imagine. It could contain regions still undergoing inflation, expanding exponentially, while our observable patch has long since transitioned to slower expansion. The multiverse hypothesis, in some formulations, suggests that different regions of the actual universe have nucleated into separate pocket universes, each with its own physical laws, forever isolated from one another by inflating space. Within our observable sphere, we have catalogued approximately 2 trillion galaxies, each containing hundreds of billions of stars. We have mapped the cosmic web, traced the filaments and voids, identified superclusters spanning hundreds of millions of light years. We have detected the cosmic microwave background, measured its temperature to 6 decimal places, extracted from its subtle variations the parameters that govern cosmic evolution. All of this knowledge, all of this painstaking observation and analysis describes only a finite bubble of visibility in what may be an infinite expanse. The observable universe contains roughly 10 to the 80 atoms, a number so large it defies intuition. Yet this staggering quantity may represent an infinitesimal fraction of the actual total. If the universe is infinite, it contains infinite matter, infinite galaxies, infinite possibilities. Somewhere beyond our horizon, the laws of probability suggest every possible configuration of matter exists. Every possible arrangement of atoms, every possible history, every possible outcome plays out in some distant region we will never observe. This is not mysticism, but mathematics, the inevitable consequence of infinite space and finite possible configurations. And yet we remain here, on a small planet orbiting an ordinary star, peering out at our cosmic bubble with instruments of extraordinary precision. The observable universe is our universe, the only one we can study, the only one whose secrets we can hope to unlock. Beyond the horizon, the actual universe continues in silence, its contents forever beyond our reach, its nature forever beyond our knowledge. We are islanders on a sphere of light, surrounded by an ocean of darkness that extends, perhaps, without end. The ocean of darkness that surrounds our observable sphere was not always so vast, so unreachable. In the earliest fraction of a second after the Big Bang, the universe underwent a transformation so rapid and so extreme that it created the very isolation we now experience. This event, known as cosmic inflation, stretched space itself faster than light could travel, tearing apart regions that had once been in contact and flinging them to distances so great that they can never communicate again. To understand inflation is to understand why the universe appears the way it does, and why most of it will remain forever hidden. The theory emerged not from a desire to explain remoteness, but from puzzles in the cosmic microwave background itself. When astronomers measured the temperature of that ancient light across the entire sky, they found something remarkable. It was almost perfectly uniform. Regions on opposite sides of the sky, separated by billions of light years, showed temperatures that differed by only 1 part in 100,000. This uniformity presented a profound problem. Consider 2 points on opposite sides of the observable universe. The light we see from each has traveled for 13.8 billion years to reach us. But those 2 points are separated from each other by more than 90 billion light-years in the current expanded universe. In the standard model of cosmic expansion, there was never enough time for light, or any signal, to travel between those regions. They exist outside each other's light cones, causally disconnected since the beginning. Yet somehow, they reached the same temperature, the same density, the same conditions, as if they had once been in thermal equilibrium. This is the horizon problem, and it has no solution within ordinary expansion. 2 regions that have never been in contact cannot coordinate their temperatures any more than 2 strangers on opposite sides of the Earth could simultaneously decide to set their thermostats to exactly the same value without ever communicating. The uniformity of the cosmic microwave background demands an explanation. Inflation provides that explanation through a mechanism both elegant and violent. In the first tiny fraction of a second after the Big Bang, specifically between approximately 10 to the negative 36th seconds and 10 to the negative 32nd seconds, the universe expanded exponentially. During this brief interval, space itself stretched by a factor of at least 10 to the 26th power, possibly far more. A region smaller than a proton inflated to a size larger than the current observable universe in less than a trillionth of a trillionth of a trillionth of a second. The numbers strain comprehension. Before inflation, the entire observable universe, all 93 billion light-years of it, was contained in a volume smaller than an atom. Every galaxy we can see, every photon of the cosmic microwave background, every particle of matter in our cosmic horizon, once occupied a space so small that light could easily traverse it. In that primordial moment, all these regions were in causal contact. They could exchange energy, reach thermal equilibrium, and establish the uniform conditions we observe today. Then inflation began. Driven by a hypothetical field called the inflaton, space expanded faster than light itself. This does not violate relativity, for nothing moved through space faster than light. Instead, space itself stretched, carrying matter and radiation along with it like raisins in rising bread dough. The expansion was not motion in the conventional sense, but the creation of new space between every point, everywhere, simultaneously. During inflation, the expansion rate was not constant but exponential. The universe doubled in size, then doubled again, then again, each doubling occurring in an inconceivably small fraction of a second. After approximately 60 to 70 doublings, inflation ended. The inflaton field decayed, releasing its energy as a flood of particles and radiation in an event called reheating. This energy became the hot, dense plasma that would eventually cool into the cosmic microwave background, and later into galaxies, stars, and planets. But the consequences of inflation extend far beyond explaining the uniformity we observe. Inflation created isolation on a scale that dwarfs even the cosmic horizon. Regions that were once neighbors, once in contact, once sharing the same temperature and density, were flung apart so rapidly that they crossed beyond each other's horizons during the inflationary epoch itself. They became causally disconnected not billions of years later, but in that first fraction of a second. The mathematics of inflation suggests that the actual universe is incomprehensibly larger than the observable portion. If inflation lasted even slightly longer than the minimum required to solve the horizon problem, the total universe could be 10 to the power of 1,000 times larger than what we can see. Some models suggest it could be infinite. In either case, the observable universe represents an infinitesimal fraction of the whole, a single bubble in an ocean of space that extends beyond all possible measurement. Within this vast, inflated space, regions exist that were once part of our cosmic neighborhood. Particles that interacted with particles that would eventually become part of our bodies now reside in volumes of space so distant that the expansion of the universe has carried them beyond any possible future contact. If we could somehow freeze the expansion and travel at the speed of light, we would never reach them. The space between us grows faster than we could ever cross it. This is causal disconnection in its most absolute form. It is not merely that these regions are far away, or that light from them has not yet reached us. It is that they are receding so rapidly, and have been since the first instant of cosmic time, that no signal, no particle, no influence of any kind can ever pass between us. They are as isolated from our universe as if they existed in a separate cosmos entirely. The inflationary model makes specific predictions that observations have confirmed with remarkable precision. The tiny quantum fluctuations in the inflaton field, stretched to cosmic scales by the exponential expansion, became the seeds of all structure in the universe. These fluctuations appear in the cosmic microwave background as slight temperature variations, and their statistical properties match inflationary predictions to extraordinary accuracy. The spectrum of these fluctuations, their distribution across different angular scales, their Gaussian nature, all align with what inflation predicts. Yet inflation also implies something profound about the nature of existence beyond our horizon. If inflation occurred once in our region of space, the same physics suggests it should occur elsewhere, perhaps continuously. This leads to the concept of eternal inflation, a scenario in which inflation never truly ends, but continues in some regions even as it stops in others. Our observable universe would then be just one bubble in an infinite foam of universes, each bubble nucleating from the inflating background, each expanding and cooling into its own cosmic domain. In eternal inflation, new universes form continuously, budding off from the inflating substrate like bubbles in boiling water. Each bubble universe has its own Big Bang, its own cosmic microwave background, its own galaxies and stars. The bubbles expand, but the space between them expands faster, ensuring they never collide, never interact, never exchange information. They are causally disconnected not just from us, but from each other. An infinite archipelago of cosmic islands separated by eternally inflating seas. The regions created by inflation are not merely distant, but fundamentally unreachable. Even if the expansion of the universe were to somehow stop, even if we could travel at the speed of light for infinite time, we could not reach these disconnected domains. They were separated from us before light itself had time to establish contact, before causality could weave its threads between our location and theirs. They exist in the same space-time, governed by the same physical laws, yet they are as inaccessible as if they occupied different dimensions entirely. And so inflation, the mechanism that explains the uniformity of our observable universe, simultaneously guarantees that most of the universe will remain forever unknown. It solved the horizon problem by ensuring that our visible cosmos was once small enough to reach equilibrium, but in doing so, it created horizons of a different kind, boundaries not of observation but of causality itself. Beyond these boundaries, space continues, matter exists, physics operates, but none of it can ever affect us or be affected by us. We are not merely isolated by distance or by the finite speed of light. We are isolated by the very fabric of space-time, stretched beyond reconnection in the first heartbeat of cosmic time. Light itself carries the memory of cosmic expansion written into its very wavelength. Every photon traveling across the universe stretches as space expands, its wavelength growing longer, its energy diminishing with each passing billion years. This process, redshift, transforms the character of light so profoundly that photons emitted as brilliant ultraviolet radiation eventually fade into infrared, then into microwaves, and ultimately into radio waves so long and so weak that they become indistinguishable from the quantum noise of empty space itself. The physics of this transformation follows directly from the expansion of space-time. When a photon leaves a distant galaxy, its wavelength might measure 400 nanometers, placing it in the violet portion of the visible spectrum. But as that photon travels, the space it moves through stretches. After 1 billion years of travel, the wavelength has grown. After 5 billion years, it has stretched further still. A photon from a galaxy at redshift Z equals 2 has had its wavelength tripled since emission. What began as violet light now glows in the near-infrared, invisible to human eyes, detectable only with specialized instruments cooled to temperatures approaching absolute zero. The galaxies we observe at the edge of our detection capabilities emit light that has been stretched by factors of 10, 12, even 14. JD's GSC 14.0 at redshift 14.32 emits light that has been stretched by more than 15 times its original wavelength. Ultraviolet photons from the hot young stars in that primordial galaxy now arrive as mid-infrared radiation, their wavelengths measured in micrometers rather than nanometers. The James Webb Space Telescope detects these ancient photons precisely because its instruments operate at wavelengths of 1 to 28 micrometers, the range into which the visible and ultraviolet light of the early universe has been shifted. But this stretching does not merely change the color of light, it reduces its energy. A photon's energy is inversely proportional to its wavelength, described by the equation E equals h times c, divided by lambda, where h is Planck's constant, is the speed of light, and lambda is the wavelength. When a wavelength doubles, the photon's energy halves. When a wavelength increases by a factor of 15, the energy drops to 1/15 of its original value. The brilliant ultraviolet radiation that once ionized hydrogen atoms in the early universe now arrives as gentle infrared warmth, carrying barely enough energy to slightly elevate the temperature of a detector. This energy loss accumulates across cosmic time. Consider a photon emitted from a galaxy that now lies beyond our cosmic horizon, a galaxy whose light left when the universe was only 200 million years old. That photon has been traveling for over 13 billion years, stretching continuously as space expands. Its wavelength has grown by a factor of perhaps 20 or 30. Its energy has diminished proportionally. And as the universe continues to expand, as that galaxy recedes ever faster due to dark energy, the photons it emits today will be stretched even more severely by the time they might reach our location, if they ever do. The cosmic microwave background itself demonstrates this principle carried to its logical conclusion. The photons of the CMB were emitted as visible and near-infrared light, with temperatures around 3000 Kelvin, glowing like the surface of a red dwarf star. But over 13.8 billion years of cosmic expansion, those photons have been stretched by a factor of approximately 1,100. Their wavelengths have grown from roughly 1 micrometer to over 1 millimeter. Their temperature has dropped from 3000 Kelvin to 2.725 Kelvin, barely above absolute zero. What was once a sky filled with the orange-red glow of cooling plasma is now a faint microwave hum, detectable only with radio telescopes and satellite observatories. This fate awaits all light in an expanding universe. The photons from distant galaxies, the gamma rays from ancient stellar explosions, the radio waves from primordial hydrogen clouds, all of them stretch as they travel, losing energy to the expansion of space itself. There is no mechanism to recover this lost energy. It does not transfer to some other form or accumulate somewhere in the cosmos. The energy simply becomes less concentrated, spread across ever longer wavelengths, diluted by the growing volume of the universe. For galaxies near the edge of our observable universe, this process has already rendered them nearly invisible. At redshift 12 or 13, the brightest emission lines of hydrogen and oxygen have shifted from ultraviolet wavelengths into the mid-infrared. The continuum emission from stellar populations has moved from visible light into wavelengths that even Webb struggles to detect with precision. Each additional unit of redshift pushes these signals further into the infrared, then into the far infrared, then into the sub-millimeter regime, where Earth's atmosphere becomes opaque and only space-based observatories can observe. But the expansion of the universe is accelerating. Dark energy, comprising roughly 68% of the cosmic energy density, drives space to expand faster with each passing epoch. This acceleration means that distant galaxies recede from us at ever-increasing velocities. A galaxy at the edge of our current observable universe recedes at approximately 3 times the speed of light due to the expansion of intervening space. As dark energy continues to dominate, this recession velocity will only increase. The consequence for light is profound. Photons emitted today from galaxies at the cosmic horizon face a journey that grows longer even as they travel. The space ahead of them expands faster than they can cross it. These photons will never reach us. They are already lost, their light stretched toward infinite wavelength, their energy approaching zero, their information content diluted beyond any possibility of recovery. Even galaxies currently within our observable universe will eventually fade from view. As cosmic expansion accelerates, galaxies that we can see today will cross beyond our horizon. Their light will stretch to longer and longer wavelengths. First, they will fade from visible observation, detectable only in infrared. Then they will dim in infrared, visible only in radio wavelengths. Eventually, their photons will stretch to wavelengths longer than the observable universe itself, their energy reduced to values smaller than the quantum uncertainty of empty space. This process unfolds slowly by human standards, but inexorably by cosmic ones. Over the next 100 billion years, the accelerating expansion will push all galaxies beyond the local group, past our cosmic horizon. The light from the Virgo cluster, currently 54 million light-years away, will redshift beyond detection. The great galaxy clusters of the Coma and Perseus superclusters will fade into invisibility. The cosmic web of filaments and voids that currently structures the observable universe will stretch and dim until nothing remains visible beyond our immediate galactic neighborhood. The final photons from these departing structures will arrive with wavelengths measured in meters, then kilometers, then astronomical units. Their energy will fall below the detection threshold of any conceivable instrument. They will become indistinguishable from the vacuum fluctuations that permeate all of space. Their information content erased not by any physical barrier, but by the fundamental limits of measurement in a quantum universe. And so the light that carries the history of the cosmos gradually loses its voice. The photons that witnessed the birth of the first stars, the formation of the first galaxies, the ignition of the first quasars, all of them fade as they travel, their stories growing fainter with each billion years of expansion. The universe does not hide its past behind walls or barriers. It simply stretches that past into silence, red-shifting the ancient light until it whispers too softly to hear, until it glows too dimly to see, until it carries too little energy to disturb even a single electron in the most sensitive detector ever built. Yet even as distant light fades beyond detection, Even as ancient photons stretch into invisibility, the universe reveals its hidden depths through another messenger entirely. Matter itself carries signatures of influences we cannot see, gravitational tugs from structures that lie beyond the cosmic horizon, forces that reach across the observable boundary to shape the motions of everything within our view. In 2008, astronomers analyzing the movements of galaxy clusters across vast regions of space discovered something unexpected. Hundreds of clusters, spanning distances of billions of light years, appeared to share a common motion, a coherent flow toward a particular region of the sky that could not be explained by any visible structure. This phenomenon, dubbed dark flow, suggested that something enormous, something far beyond the edge of our observable universe, was exerting gravitational influence on matter within our cosmic horizon. The measurements came from studying the cosmic microwave background itself. As galaxy clusters move through space, they interact with the ancient photons of the CMB through a process called the kinetic Sunyaev-Zeldovich effect. Hot electrons in the cluster gas scatter the microwave photons, shifting their frequencies slightly depending on whether the cluster moves toward or away from us. By analyzing these tiny frequency shifts across hundreds of clusters, researchers detected a bulk motion of approximately 600 to 1,000 kilometers per second, all pointing roughly towards the constellations Centaurus and Hydra. This velocity is remarkable not for its magnitude alone, but for its coherence. Individual galaxy clusters move in many directions, pulled by nearby superclusters, falling into cosmic filaments, orbiting within their local gravitational environments. Random motions average out over large samples, but dark flow appeared as a systematic drift, a shared velocity component that persisted even when local gravitational influences were accounted for, suggesting an external cause beyond anything visible in our surveys. The implications were profound and controversial. If dark flow is real, it points toward mass concentrations that existed before inflation, structures that were pushed beyond our horizon during the exponential expansion of the early universe, but whose gravitational influence still reaches us across that boundary. Gravity, unlike light, is not limited by the cosmic horizon in the same way. Gravitational effects propagate at the speed of light, but the gravitational field of a distant mass was established when that mass was much closer, before expansion carried it beyond our view. We feel the gravitational echo of objects we can no longer see. The Great Attractor, discovered in 1986, offered a closer example of hidden gravitational influence. Located approximately 250 million light-years away in the direction of the Centaurus supercluster, this region exerts a powerful pull on our local group and thousands of other galaxies. For years, the Great Attractor's true nature remained obscured because it lies behind the zone of avoidance, the band of the Milky Way's disk where the dust and stars block our view of distant objects. We could measure its gravitational effect long before we could see what caused it. Eventually, X-ray observations and infrared surveys pierced the galactic obscuration, revealing the Norma cluster and surrounding structures as the primary source of the attraction. The Great Attractor itself turned out to be part of an even larger flow toward the Shapley supercluster, a massive concentration of galaxies lying 650 million light-years away. Our entire local region of space, encompassing the Virgo supercluster and the newly defined Laniakea supercluster, with its 100,000 galaxies spanning 520 million light-years, streams toward Shapley at velocities of several hundred kilometers per second. But dark flow, if confirmed, would dwarf even these enormous structures. The coherent motion it implies would require mass concentrations far exceeding anything within the observable universe, structures that formed from primordial density fluctuations and were subsequently inflated beyond our cosmic horizon. These hypothetical objects might be superclusters of superclusters, vast overdensities containing the mass of millions of Milky Ways, forever invisible yet still gravitationally connected to our observable patch of cosmos. The controversy surrounding dark flow centers on the difficulty of the measurements and the challenge of separating genuine bulk motion from systematic errors. Different research groups analyzing the same CMB data have reached conflicting conclusions. Some confirm the signal, finding persistent bulk flows extending to distances of 2.5 billion light-years or more. Others find no statistically significant detection, attributing the apparent flow to instrumental effects or incomplete removal of local gravitational influences. The Planck satellite's precise measurements of the CMB placed upper limits on bulk flows that seemed to contradict some earlier claims, yet the debate continues as new analysis techniques are developed. Whether or not dark flow proves to be real, the concept illuminates a profound truth about our cosmic situation. The observable universe is not gravitationally isolated. The horizon that limits our vision does not limit gravitational influence. Mass beyond our view can still tug on mass within it, creating motions and flows that hint at structures we will never directly observe. The universe we see is embedded in a larger gravitational environment, shaped by forces whose sources lie forever beyond the reach of any telescope. This gravitational connection across the horizon creates a kind of cosmic archaeology, where the motions of visible matter preserve information about invisible structures. Just as the orbit of a planet reveals the mass of its unseen star, the bulk flows of galaxy clusters might reveal the distribution of matter beyond our cosmic horizon. The universe writes its hidden geography in the velocities of the objects we can see, encoding information about regions we can never image into the trajectories of the galaxies we observe. The physics of this trans-horizon influence involves the finite speed of gravity and the history of cosmic expansion. When the universe was young and small, regions that are now beyond our horizon were once much closer, their gravitational fields overlapping with our own cosmic neighborhood. As expansion accelerated, these regions receded beyond the horizon, but the gravitational relationships established in that earlier, denser era persist. We feel the pull of objects that were once our neighbors, even though expansion has carried them into permanent invisibility. And so the gravitational echoes of that ancient connected era continue to shape the motions we observe today, even as the sources of those influences recede forever beyond detection. But this recession carries with it a profound consequence for the future of observation itself. The universe is not merely expanding, it is accelerating, driven by the mysterious pressure of dark energy that permeates all of space. This acceleration means that the cosmic horizon is not static. It is shrinking, drawing ever closer, and with it comes an inevitable conclusion. The objects we can see today will not always be visible. The final photons from distant galaxies are already on their way, and eventually they will stop arriving altogether. The physics of this cosmic dimming begins with the Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec. This value describes how quickly space expands at different distances. For every megaparsec of separation, roughly 3.26 million light-years, galaxies recede from us at an additional 70 kilometers per second. At a distance of about 14 billion light-years, this recession velocity equals the speed of light itself. Beyond this distance lies the Hubble sphere, the boundary where space expands faster than light can travel through it. But the Hubble sphere is not the true horizon of visibility. Light emitted from galaxies just beyond this boundary can still reach us, because the photons, once launched, travel through regions of space that expand more slowly as they approach. The true cosmic horizon, the particle horizon, lies farther out, at approximately 46.5 billion light-years in every direction. This is the edge of the observable universe, the surface beyond which no signal has ever had time to reach us since the Big Bang, 13.8 billion years ago. The critical distinction is between the particle horizon, which marks the farthest distance from which light has had time to arrive, and the event horizon, which marks the farthest distance from which light emitted today will ever reach us in the infinite future. Due to accelerating expansion, the cosmic event horizon currently lies at roughly 16 billion light-years. Any photon emitted from beyond this distance right now will never reach Earth, no matter how long we wait. The space between us and that photon will expand faster than the photon can cross it, like a swimmer struggling against an ever-strengthening current. This event horizon is drawing closer. As dark energy continues to accelerate expansion, the distance at which recession velocity exceeds light speed shrinks. Galaxies that are currently within our observable universe, currently sending photons that will eventually reach our telescopes, will one day cross the event horizon. When they do, the photons they emit will no longer be able to reach us. We will receive their final light, and then nothing more, ever again. Consider the Coma Cluster, a massive gathering of over 1,000 galaxies located approximately 321 million light-years away in the constellation Coma Berenices. Today, light from the Coma Cluster reaches us easily, carrying information about its member galaxies, its hot intracluster gas at temperatures exceeding 100 million Kelvin, its gravitational dynamics. But in the far future, roughly 150 billion years from now, the Coma Cluster will cross our event horizon. The last photons it emits before that crossing will travel toward us, but they will be fighting against accelerating expansion. These final photons will be stretched to extraordinary wavelengths, their energy diminishing with each passing eon until they fade below any possible detection threshold. The mathematics of this fading follows from the redshift equation. As a galaxy approaches the event horizon, its redshift increases without bound. A galaxy at redshift z equals 10 has had its light stretched by a factor of 11. Wavelengths that began as ultraviolet have shifted into the infrared, but a galaxy at redshift z equals 100 has had its light stretched by a factor of 101, pushing visible light into radio wavelengths. And as redshift approaches infinity, the photons stretch beyond any conceivable detection, their wavelengths exceeding the size of the observable universe itself. The local group, our immediate galactic neighborhood containing the Milky Way, Andromeda, and roughly 80 smaller galaxies, will remain gravitationally bound as the universe expands. Gravity within this region is strong enough to overcome cosmic expansion, holding these galaxies together even as the rest of the universe recedes. In approximately 4.5 billion years, the Milky Way and Andromeda will merge into a single large elliptical galaxy, sometimes called Milkomeda or Milkdromeda. This merged system, along with its satellite galaxies, will persist as an island of matter in an increasingly empty cosmos, but everything beyond the local group will eventually vanish. The Virgo cluster, currently 54 million light-years distant and containing over 1,300 member galaxies, will recede beyond the event horizon. The Fornax cluster, the Centaurus cluster, the great superclusters that form the cosmic web, all will cross that invisible boundary one by one, their light fading into undetectable whispers. The timeline of this cosmic loneliness stretches across trillions of years. In roughly 100 billion years, all galaxies beyond the local group will have redshifted beyond visibility in optical wavelengths. In 1 trillion years, even their radio emissions will have faded below detection. The cosmic microwave background itself, that ancient wall of light from 380,000 years after the Big Bang, will stretch to wavelengths longer than the observable universe, becoming fundamentally undetectable. Future astronomers, if any exist in that distant era, will look out at a universe that appears to contain only their own galaxy. The evidence of the Big Bang, of cosmic expansion, of the billions of galaxies that once filled the observable universe, all of it will have faded beyond recovery. The night sky will contain only the stars of the local group, burning through their nuclear fuel, eventually dying one by one as the universe approaches heat death. The last external photons to reach such observers will come from the most distant galaxies currently visible, those ancient systems at redshifts of 10 or higher. These photons, already 13 billion years old when they arrive at our telescopes today, will continue traveling for billions of years more, stretching ever longer, growing ever fainter. The final detectable photon from the external universe will arrive, and then silence. The cosmic horizon will have closed completely around the local group, sealing it within an observational bubble from which no information about the greater universe can ever again be extracted. This fate is not speculation, but mathematical certainty, given our current understanding of dark energy and cosmic expansion. The universe is not merely large and ancient, it is actively erasing itself from view, withdrawing its contents beyond the reach of any possible observation. The photons arriving at our telescopes tonight are precious beyond measure, carrying information that will never be available again once their sources cross the event horizon. And so we find ourselves in a privileged epoch, a window of cosmic time when the universe still reveals its structure, its history, its vast populations of galaxies and clusters and superclusters. The light we gather now is irreplaceable, a record of cosmic evolution that future observers will never be able to reconstruct. The final photons are not merely the last signals from distant objects, they are the closing pages of a book that the universe itself is slowly, inexorably shutting forever.